Now there are questions on simple combination, which are if we have n distinct objects, and from n distinct objects, if we have to select r distinct objects, then it can be done in simply NC R ways. And then there'll be many problems, like some particular things are always selected, some are not selected. All those questions, they'll be considered in combinations. Now generally in PNC, there is a doubt when to multiply and when to add. So if we have this AND case, then we need to multiply. And if we have this OR case, in that case, we have to add them. Say for example, there are 6 boys and 5 girls. Suppose we need to take 3 boys and 2 girls. Now 3 boys out of 6 boys can be selected in 6C3 ways, and 2 girls from 5 can be selected in 5C2 ways. Now do we need to multiply or do we need to add? Now since we need 3 boys and 2 girls, we need to multiply. So this value will be 6, 5, 4, 3, 2, 1, and this is into 10. So this value will be 200. Now suppose the question is, there are 6 boys and 4 girls, and we need to select 4 students so that it has at least 3 girls. Now there will be 2 cases possible. Either it will be 1 boy and 3 girls, or all 4 girls. Now 1 boy is 6C1 and 3 girls, so which is 4C3, or 4 girls. 4 girls is 4C4. Now since we have this OR here, now we'll add them. So if we have AND case, we'll multiply, and if we have OR case, then we'll add them. Now the question is, in a high school, a committee has to be formed from a group of 6 boys, M1 to M6, and 5 girls, G1 to G5. Let alpha 1 be total number of ways in which committee can be formed such that committee has 5 members having exactly 3 boys and 2 girls. So alpha 1 is exactly 3 boys. So from these 6 boys, we have to select 3 boys, and it can be done 6C, 3 ways, and then 2 girls. So 5 from 2 is 5C2. So it will be 20 into 10, and there will be 200. So this P, it matches with 4. So P, it matches with 4. Now alpha 2 is the total number of ways in which the committee can be formed such that committee has at least 2 members and having an equal number of boys and girls. So it could be 1 boy, 1 girl, or 2 boys, 2 girls, or 3 boys, 3 girls, or 4 boys, 4 girls, and finally 5 boys and 5 girls. Now this is 6C1, 5C1 plus 6C2, 5C2 plus 6C3 into 5C3, 6C4 into 5C4 plus 6C5 into 5C5. Now 6C1 is 6, 5C1 is 5, 6C2 is 15 into 10, 20 into 10, 15 into 5, and then 6 into 1, which is 461. That means this Q, it matches with 6. So Q matches with 6. Now this third case is, let alpha 3 be total number of ways in which the committee can be formed such that committee has 5 members and at least 2 of them are girls. So this alpha 3 is 3 boys, 2 girls, or 2 boys, 3 girls, or 1 boy, 4 girls, or all 5 girls. Now this is 6C3 into 5C2, 6C2, 5C3, 6C1, 5C4 plus 5C5. Now this is 20 into 10. This is 15 into 10, and this is 6 into 5 plus 1, which is 381. So that means this R, it matches with 5. So this R, it matches with 5. So clearly answer has to be this option C, but still we'll solve this option 4, alpha 4. Now alpha 4 is total number of ways in which the committee can be formed such that the committee has 4 members having at least 2 girls such that both M1 and G2 are not in the committee together. So committee should have at least 2 girls. So this alpha 4, it can be 2 girls, 2 boys, or 3 girls, 1 boy, or all 4 girls. Now we have to select 2 girls and 2 boys such that it should not include M1 and G1. So what we'll do is from total, which is 6C2 into 5C2, we'll subtract that case where we have selected both M1 and G1. Then it will be 5C1 into 4C1 plus, now 3 girls and 1 boy, it will be 5C3 into 6C1 minus this case when 1 girl and 1 boy is selected. So it will be 4C2 and plus 5C4. Now this is 15 into 10, 150 minus 20 plus, now this is 60 minus 6 and plus 5. So this value will be 215 minus 26, and which is 189. That means this S, it matches with 2. So the correct option is this option C. Now question number 8 is, take R such that R lies between 1 and n and consider all subsets of R elements of the set 1 to up to n. Each subset has a smallest element. Now let F and R be the arithmetic mean of all these smallest elements. Then prove that F and R equals n plus 1 upon R plus 1. Now first we'll find total number of subsets. Now total number of subsets with R elements will be simply NCR. So we have n elements and we can choose R distinct elements in NCR ways. Now then we'll find number of subsets in which the smallest element is 1. If the smallest element is 1, then we need to choose remaining R minus 1 elements from n minus 1 elements. So there will be n minus 1 C R minus 1 such sets. So n minus 1 C R minus 1 sets will have 1 as its minimum element. And the same way, number of sets having 2 as minimum element will be n minus 2 C R minus 1. Having 3 as minimum element will be n minus 3 C R minus 1, and it will continue up to R minus 1 C R minus 1 when we have n minus R plus 1 as the smallest element. Now we have n minus 1 C R minus 1 ones, n minus 2 C R minus 1 twos, n minus 3 C R minus 1 threes, and R minus 1 C R minus 1 n minus R plus 1 numbers, and total number of numbers is NCR. If we find the arithmetic mean and we write it as F and R, then F and R simply will be 1 plus 1 plus 1 n minus 1 CR minus 1 times, so it will be 1 into n minus 1 CR minus 1 plus 2 into n minus 2 CR minus 1, 3 into n minus 3 CR minus 1 up to n minus R plus 1 R minus 1 CR minus 1 upon total number of elements, which is NCR. Now we can rearrange the series in the numerator as F n R equals n minus 1 CR minus 1 plus n minus 2 CR minus 1 up to R minus 1 CR minus 1. Now plus this second series, which is from n minus 2 CR minus 1, n minus 3 CR minus 1 up to R minus 1 CR minus 1, and this series it goes up to this last element, which is R minus 1 CR minus 1 upon NCR. Now we can write R minus 1 CR minus 1 as RCR, and the term before this will be RC R minus 1. Now n is same, R differs by 1, it will be r plus 1 CR. And when we continue adding this series, the sum of this series will be NCR. In the same way, sum of this series will be n minus 1 CR, n minus 2 CR, and here will be r minus 1 CR minus 1 upon NCR. Now we again use the same property here. The series again sums to n plus 1 CR plus 1 upon NCR. So this FNR, it is n plus 1 CR plus 1 upon NCR. Now this is factorial n plus 1 factorial r plus 1 factorial n minus r upon factorial n factorial r factorial n minus r. I will cancel. Now this factorial n and factorial n plus 1, it will give us n plus 1, and factorial r plus 1 upon factorial r will give us r plus 1. So from here we can say value of f and r is n plus 1 upon r plus 1, which is what we need to prove in this question. Now here the question is, a class contains 4 boys and G girls. Every Sunday, 5 students, including at least 3 boys, go for a picnic to Apughar, a different group being sent every week. During the picnic, the class teacher gives every girl in the group a doll. The total number of dolls distributed was 85. Then find the value of G. Now we have 4 boys and G girls in class, and every Sunday 5 students, in which it has at least 3 boys. So we'll have 2 cases. Either it will be 3 boys and 2 girls, or it will be 4 boys and 1 girl. Now number of distinct ways in which we can choose 3 boys and 2 girls. It is given by 4C3 into GC2, and here it will be 4C4 into GC1. Now in these strips, since there are 2 girls, so number of dolls required will be this case into 2, and plus here, since there is only 1 girl, it will be into 1, and this value, it is equal to 85. Now 4C3 is 4, 4 into 2 is 8. So this is 8G, G minus 1 by 2 plus G, it is equal to 85. Now this is 4, so it will be 4G square minus 3G minus 85 equals 0, which is 4G square minus 20G plus 17G minus 85 equals 0. That means value of G is simply 5. So number of girls in the class is 5, and that's your option B.
Now let us take another question, in which is, suppose there are n lines and no 2 of which are parallel and no 3 are concurrent. If their points of intersection are joined, then we need to show that number of fresh lines, new lines thus formed is n, n minus 1, n minus 2, n minus 3 by 8. So what you have is, we have n lines. So L1, L2, L3, and then we have this Ln. So first we'll find out how many points of intersections are there in this given condition. So number of points of intersection will be NC2, because no 2 lines are parallel and no 3 of them are concurrent. So number of points of intersection will be simply NC2, and which is n into n minus 1 by 2. I'll say, suppose this is n. Now if I'll take these m points and if I'll start joining these m points, then number of lines that can be formed is simply MC2, which is m minus 1 by 2. So I'll put the value of n here. So here I'll get n minus 1 by 2 into n minus 1 by 2 minus 1, and then whole divided by 2. So it will be n n minus 1, and here will be n square minus n minus 2 upon 8. So it will be n minus 1, here will be n minus 2, n plus 1, and then whole divided by 8. Now these are number of lines that can be formed from these m points, but we need to find number of fresh lines or number of new lines that can be formed. So what's happening here is, out of these n minus 1, n minus 2, n plus 1 upon 8 lines, some of the lines will be old lines, like one of either L1, L2, L3 or Ln, and then there will be some new lines. So from these total lines, we have to subtract or we have to exclude all the old lines or the previous lines. So now what we are doing it is, suppose I consider this line L1. Now on this L1, how many points of intersections will be there? Now this L1 will intersect every other line. So it will intersect L2, L3, L4 and then Ln. So there will be n minus 1 points of intersection on this line L1. So if I select any 2 points on this line, then every time when I'm drawing a line, I'll end up getting L1 and not a new line. So in how many ways can I get old line L1? So then it will be n minus 1 C2. In the same way, suppose I consider it for L2. For L2 again, it will intersect at n minus 1 points, and from these n minus 1 points, again the number of ways in which I'll get this L2 is n minus 1 C2, and again for Ln, again there will be n minus 1 points of intersection. So again I'll get this line, nth line in n minus 1 C2 ways. So number of fresh lines will be given by this total lines n minus 1, n minus 2, n plus 1 by 8, and then minus n minus 1 C2 for L1, n minus 1 C2 for L2, n minus 1 C2 for Ln. So it will be n into n minus 1 C2. If I'll simplify, I'll write it as n minus 1, n minus 2, n plus 1 upon 8, and then minus, and this is n minus 1, n minus 2 by 2. Now here I'll take n minus 1, n minus 2 by 2 common. So if I take it common, then I'm left with n plus 1 upon 4, and here it will be 1. So now it will be n minus 1, n minus 2, n minus 3 whole divided by 8. So number of new lines or number of fresh lines thus formed is n minus 1, n minus 2, n minus 3 whole divided by 8. So this is how we solve these questions.
Today we'll discuss another very important fundamental in permutations and combinations, and which is consecutive and non-consecutive selection. Now consecutive selection is very simple. Suppose we have n objects in a row, say A1, A2, A3 and An, and from these n objects we have to select, suppose, r consecutive objects. It can start from A1 and then all the way up to AR. Next one, it can start from A2 and it can go all the way up to AR plus 1. Then again for A3. So in this way we can keep choosing these r consecutive steps starting from A1 to n minus r plus 1. So the last possibility of r consecutive objects which contains these last r elements will start from an minus r plus 1. So if we have to select r consecutive objects from n arranged objects, then it can be done in n minus r plus 1 ways. So if we take very basic example, suppose we have 8 objects, A1, A2, A3, A4, A5, A6, A7 and A8. In how many ways we can select one consecutive object? It can be done in 1, 2, 3 up to 8 ways, which is 8 minus r, which in this case is 1 plus 1, and that is 8 ways. Now what about two consecutive objects? A1, A2, A2, A3, A3, A4
and finally A7 and A8. So it starts with A1 and it ends at A7. So two consecutive objects. It can be done in 7 ways, which again is 8 minus 2 plus 1. So if we have n objects arranged in a row and we have to select r consecutive objects, then it can be done in n minus r plus 1 ways. Now what if these n objects, they are arranged on a circle? So suppose we have a circle and then we have these n objects a1, a2, a3 and up to an. They are all arranged in a circle. Now in how many ways we can select r consecutive objects? So suppose we need one consecutive object. So it'll start with a1 and then it'll be a2 and then a3 and then it will be an. So if we have to select one consecutive object on a circle, it can be done in simply n ways. Now what about two at a time? So it'll start with a1, so it'll be a1 a2, a2 a3, a3 a4 and the last one will be an a1. So it'll be a1 a2, a2 a3 and then finally it'll be an a1. So here it starts with a1 and it ends with an. So the total number of ways in which we can select two consecutive objects is simply n again. Now what about three consecutive objects? So it starts with a1 a2 a3, a2 a3 a4 and finally it'll be an a1 a2. So again starts with a1 and ends with an. So again for three consecutive objects it is simply n. So from here we can simply say if n objects are arranged on a circle, then from these n objects we have to select r consecutive objects. Then it can be done in simply n ways. So if the objects are arranged in a row, then total number of r consecutive selections is n minus r plus 1. But on a circle, the total number of ways of selecting r consecutive objects is simply n. Now let us take up an example. Say for example, we have a chessboard having 8 cross 8 squares. Now on this chessboard, we need to find how many 2 cross 2 squares can be selected. We need to find out on a chessboard how many 2 cross 2 squares are possible. Now how do we do that? So if we have to find 2 cross 2 squares, we need 2 squares which are connected horizontally and 2 squares which are connected vertically. So we need to find number of ways of selecting 4 squares such that 2 of them are consecutive horizontally and 2 of them are consecutive vertically. So we know that out of n objects, if we have to select r consecutive objects, it can be done in n minus r plus 1 way. So if we have to select 2 horizontal consecutive squares, it can be done in n, which in this case is 8, minus r, we need 2 consecutive, so which is 8 minus 2 plus 1. So it will simply be 7 ways. Now in how many ways we can select? 2 vertical consecutive squares. So again we have 8 squares and we need to select 2 consecutive. It can be done in 8 minus 2 plus 1, which again is 7 ways. So the total number of ways of selecting 2 cross 2 squares will be 7 into 7 and there will be 49 ways. So on a chessboard we can select 2 cross 2 squares in 49 ways. Now if we extend this question and we say find total number of squares that can be formed on a chessboard, So we can start with all 1 cross 1 squares. It can be done in 8 cross 8 ways. Now what about 2 cross 2? 2 cross 2, it is 7 and 7. So it will be 7 into 7 ways. What about 3 cross 3? For 3 cross 3, we need 3 horizontally connected and 3 vertically connected. So for 3 horizontally connected, it will be 8 minus 3 plus 1, which again is 6. So it will be 6 into 6. For the next one, it will be 5 into 5. And then finally, it will be all 8 and 8. So there will be 8 cross 8 square, and that is only 1 square. So that is 1 into 1. So the total number of squares on a chessboard is given by 1 square, 2 square, 3 square, and it goes all the way up to 8 square, which is n plus 1, 2n plus 1 by 6, which is 204. So the total number of squares on a chessboard will be 204. Another question concerning consecutive selection on a chessboard could be total number of ways of selecting 2 squares so that they have exactly one common vertex. Now 2 squares will have exactly one common vertex when they lie on a diagonal and when they are consecutive. So the problem in this question is we need to find number of consecutive selections on a diagonal of a square. We'll start with these diagonals. So for this one, there cannot be any diagonal. Now what about this? We have 2 squares, and from these 2 squares on this diagonal, we need to select 2 consecutive squares. So it can be done in n minus r plus 1, which is simply one way. Now again for the next one, there are 3 connected squares, and from these 3 connected, we have to select 2 consecutive squares. It can be done in 3 minus 2 plus 1. For the next one, it will be 4 minus 2 plus 1. Now next one, with 5, it will be 5 minus 2 plus 1, and then 6 minus 2 plus 1 plus 7 minus 2 plus 1. And then we have this main diagonal containing 8 elements. So it will be 8 minus 2 plus 1. Now after this again, it will be 7, 6, 5, 4, 3, 2, 1. So what we'll do is we'll multiply this result with 2. So the total number of ways in which we can select 2 consecutive squares on a diagonal which are inclined at an angle 45 degrees is this expression. But then there could be diagonal having an angle 135 degrees also. So what we'll do is we'll multiply this entire result by 2. So the total number of diagonals will be 2 into and then 2 into. Now this is what? This is 1, this is 2 plus 3, and then it goes all the way up to 7 minus 2 plus 1. So it will be 6 and then plus 7. So it is 4 and then n plus 1 by 2 n plus 14, which is 98 ways. So the total number of ways of selecting 2 squares on a chessboard so that they have exactly one common vertex is 98. Now let us take another problem, and that is, suppose we have a regular octagon. So it has 8 sides and 8 vertices. So the first question is we need to find number of triangles that can be formed by joining vertices of this regular octagon. The first question is total number of triangles. So we know that for a triangle, we need 3 vertex. So there are 8 vertices. From these 8, we need to select 3. It can be done in 8C 3 ways, which is 8, 7, 6, and it is 3, 2, 1, So it'll cancel. So it'll be 56. So the total number of triangles that can be formed within this octagon is 56. Now the second question is, out of all these 56 triangles, how many triangles have exactly one side common with this given octagon? Now we know that a triangle will have a side common with given octagon when we have two consecutive vertices and then we have this third vertex which is not consecutive. So the first part of this problem is number of ways in which we can select two consecutive vertices. So problem is total number of triangles having exactly one side common. So first we need to select two consecutive vertices. So we know that on a circle, if there are n objects and we have to select r consecutive objects, it can be done simply n ways. So these 8 vertices on this octagon, they are arranged on a circle. So the total number of ways in which we can select two consecutive vertices is simply 8. Now we need to select this third vertex, which has to be other than these two vertices. So 2 of them, they are already selected and these 2, they cannot be selected. So that means from these remaining 4, we have to select any one. So it can be done in 4C1 and that is 32 octagon. Now what about this problem? Total number of triangles having exactly two sides common. So if a triangle has two sides common, then all we need to do is we need to select 3 consecutive vertex on this octagon. Again on a circle, r consecutive objects, it can be done in n ways. So 3 consecutive vertex on this octagon can be selected in simply 8 ways. So total number of triangles 56. Triangles having exactly one side common 32. Triangles having exactly two sides common is 8. So finally we can find number of triangles which do not have a side common with the octagon. It will be given by total, which is 56 minus triangles with one side common and triangles with two sides common. So it'll be 56 minus 40 and there'll be simply 16. So there'll be 16 triangles which does not have a common side with this given octagon. Now here the question is, a rectangle with sides 2m minus 1 and 2n minus 1 is divided into squares of unit length by drawing parallel lines as shown in the diagram. Then number of rectangles possible with odd side lengths is. Now side lengths, if they are odd, they could be 1, they could be 3, 5 and 2m minus 1, and for the second one it could be 1, 3, 5 and 2n minus 1. Now first we will find number of ways in which we can choose this side length as 1. So from these connected 2m minus 1 squares, we have to select one square and it can be done in 2m minus 1 ways. Now if we have to select a side of length 3, then for that we need 3 connected squares, and in consecutive selections we have studied that if we have to select r consecutive from n, it is given by n minus r plus 1. So it will be 2m minus 1 minus 3 plus 1. So it will be 2m minus 3. Now the next one will be 2m minus 5 and finally will be 3 and 1. So all possible combinations of choosing odd lengths from these 2m minus 1, they are given by 1 plus 3 plus 5 up to 2m minus 1, and in the same way along this side all possible odd combinations are 1 plus 3 plus 5 up to 2n minus 1. Now we multiply them, then it represents all the possible combinations of choosing rectangle of odd sides. Now 1 multiplied with 1, it is rectangle of side 1 unit into 1 unit. 1 multiplied by 3, 1 into 3, this is 3 into 1, 5 into 3. So this product, it covers all the possible
rectangles of odd side lengths. Now we know that 1 plus 3 plus 5 up to 2m minus 1 is m square, and sum of first n odd natural numbers is n square. So this value will be m square n square. So total number of rectangles possible with odd side lengths is m square n square, and that's your option C. Now in permutations we generally arrange things, and if we have n distinct objects and we have to arrange these n distinct objects in a row, then it can be done in factorial n ways. Now say for example, suppose we have 5 boys and 4 girls. Now total number of ways in which they can be arranged in a row is factorial 9, since we have these 9 people. Now suppose the question says in how many ways they can be arranged so that all girls are together. Now once we have a question where we need things together, we'll use something called as string method. And in the string method, what we'll do is all the things that we want together, we'll tie them up with a string. So we have 5 boys and then we'll tie all these 4 girls. So now we have 6 objects, and these 6 objects, they can be arranged in factorial 6 ways. Now these 4 girls, they cannot be separated, but they can be arranged among themselves, and they can be arranged in factorial 4 ways. So this method, it is called as string method. And then we have something called as gap method, and we'll use this gap method when we need to separate things. Say for example, we need to arrange 5 boys and 4 girls in such a way that no 2 girls are together. Now when we say no 2 girls are together, what we'll do is we'll arrange all of the things. So first we'll arrange 5 boys, and 5 boys can be arranged in factorial 5 ways. So suppose we have arranged them as B1, B2, B3, B4 and B5. Now what we'll do is, since we need to separate girls, that means in between any 2 girls, there should be at least 1 boy. So we'll count the gaps. So here we have 1, 2, 3, 4, 5 and 6 gaps. So if we arrange girls in these gaps, then in between 2 girls, there'll always be at least 1 boy. Now we have 6 gaps, but we have 4 girls. So we need to choose 4 places for 4 girls. So from 6, we'll select 4 in 64 ways. And once we have 4 gaps and 4 girls, they can be arranged in factorial 4 ways. So we'll be using string method when you want things together, and we'll use gap method when we want to separate those things. Consider all possible permutations of the letter E, N, D, E, A, N, O, E, L. Now the first one is number of permutations containing the word E, N, D, E, A. So if the permutation contains E, N, D, E, A, they are all together and they are arranged in the same way. That means we have to arrange the remaining N, O, E, L. Now we have 5 objects, and these 5 objects can be arranged in factorial 5 ways. So this A, it matches with B. A, it matches with B. Now the second one is number of permutations in which letter E occurs in the first and last position. So this word, it starts with E and it also ends with E. Now we are left with N, D, E, A, N, O, L. Now we have to arrange them in between 2 E's, and it can be done in factorial 7 divided by factorial 2 ways. Now we can write factorial 7 as 6 into 7, 42 into factorial 5 divided by 2. So it will be 21 into factorial 5. That means this B, it matches with S. So B, it matches with S. Now we'll write this third one. Number of permutations in which none of the letters D, L and N occur in the last 5 positions. Now we have this 9-letter word. So we have 1, 2, 3, 4, 5, 6, 7, 8 and 9. And D, L and N, it does not appear in last 5 positions. So that means they'll appear in first 4 positions. Now we have 1 D, 1 L and 2 N's which are to be arranged in these first 4 positions, and then the remaining E, 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 A and O in the last 5 positions. Now here first 4 positions are reserved for these 4 letters. Now they can be arranged in factorial 4 divided by factorial 2 ways. Now here they can be arranged in factorial 5 divided by factorial 3 ways. So it will be simply 2 into factorial 5. So the C, it matches with Q. So C, it matches with Q. And finally, number of permutations in which letters A, E and O occur only in odd positions. So if we look at odd positions, so we have 1, 2, 3, 4 and 5. So 5 positions are reserved for E, 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 A and O, and remaining 4 they'll be reserved for D, L, N, N. So it'll be the same case. So again we'll end up getting 2 into factorial 5. So this D, it also matches with Q. So this D, it also matches with Q, and that is the answer to this question.
Now question number 3, it says, suppose Roger has 4 identical green tennis balls and 5 identical red tennis balls. In how many ways can Roger arrange these 9 balls in a line so that no 2 green balls are next to each other and no 3 red balls are together? So first we'll find in how many ways we can arrange these 4 green and 5 red balls so that no 2 green balls are together. So for that, what I'll do is I'll first arrange these 5 identical red balls. So it can be done in factorial 5 upon factorial 5, which is only one way. So I have arranged these red balls 1, 2, 3, 4 and 5. So when I have placed these 5 red balls, I have these 6 gaps. So if I'll place these green balls in either of these 6 gaps, then no 2 green ball will be together. So this is called as gap method. So out of these 6, I'll choose 4 gaps for these green balls. So it is 6C4 and then factorial 4 upon factorial 4. So it'll be simply 6C4, which is 15 ways. Now from these 15 ways, we need to eliminate or we need to exclude all those cases when 3 or more red balls are together. So we look at the arrangement again. So this is 1, 2, 3, 4 and 5. Now we need to place green balls. So if I'll place these green balls such that 1, 2, 3 and 4. Now in this case, we'll have 3 red balls together, or I can place them as 1, 2, 3, 4 and another one is 'So here we'll have 3 red again, and here also we'll have 3 red again together. So there are 3 possible configurations where these 3 red balls are together among these 15 cases. So from these 15 cases, we'll need to subtract 3 cases where these 3 red balls are together. So total number of cases when no 2 green balls are together and no 3 red balls are together is simply 12, and that's your option number D.
Now question number 28 is 2 rows of n chairs facing each other are laid out. The number of different ways that n couples can sit on these chairs such that each person sits directly opposite to his or her partner. Now we have n pair of chairs and we have n couples. Now these n couples, they can be arranged in n pairs in factorial n ways. Now in each pair, we have 2 seats. Now on these 2 seats, any one couple can be arranged in 2 ways. So for the first seat, there'll be 2 choices. For the second seat also, we'll have 2 choices. For the n seat, we'll have 2 choices. So total number of ways in which they can sit is factorial n into 2 to the power n, and that's your option C.
Question number 9, it says,
An upright path is a sequence of points x0, y0 and x1, y1, x2, y2 such that ai plus 1 minus ai is either 1, 0 or 0, 1. We need to find number of upright paths from 0, 0 to 100, 100 which pass through 1, 2. So we have this grid starting from 0, 0 and then we have these lines, horizontal and vertical lines, and we'll need to reach 100, 100 such that the path passes through 1, 2, and we need to get an upright path. So an upright path is either we go one step up or we go one step right, which is increment of 1, 0 or increment of 0, 1. So now we have this point which is 1, 2. So this is your point which is, so this is the point which is 1, 2. So first we'll find out if we'll start from 0, then in how many ways we can reach this point 1, 2. So in order to reach this point, we'll have to cross one horizontal path and two vertical paths. So what are the possible arrangements of one horizontal and two vertical paths? So total arrangements possible for one horizontal and two vertical is factorial 3 divided by factorial 2 factorial 1, and it will be simply 3. So from 0, 0 to 1, 2, so there are 3 paths possible with this upright path. Now from 1, 2, we'll need to go to 100, 100. So if we have to reach 100, 100 from 1, 2, then in that case, we'll need to cross 99 horizontal paths and we'll need to cross 98 vertical paths. Now in how many ways we can arrange these 99 horizontal and 98 vertical paths? So from 1, 2 to 100, 100, the total number of arrangements here will be 99 plus 98. So it will be factorial 197 divided by factorial 99 into factorial 98. So in how many ways we can start from 0, 0 and go up to 100 passing through 1, 2. So total number of such arrangements will be this number 3 multiplied by 197 factorial upon 99 factorial and 98 factorial, and which is simply 3 into 197 C 99, and that's your option number A. Now there will be many cases where we'll be using distribution into groups. And we'll consider distribution into unnamed groups. When I say distribution into unnamed groups, it simply means that the different groups, they cannot be identified among themselves. So suppose if I have two objects A and B, and if I distribute them, then I can distribute them as A and B. Now here B and A and B, they are considered same configuration. So these two groups, they are indistinguishable. So generally when I solve problems, I always go for unnamed distributions and thereafter I always go for arrangement. So I'll just teach you unnamed distribution. So suppose we have m plus n objects where m is unequal to m and we have to distribute them in a group of m and n. It can be done in factorial m plus n divided by factorial m factorial n ways. Now suppose we have m plus n plus p objects and we have to divide them in three groups of m, n and p, where m is unequal to n and it is unequal to p. Then we can distribute them as factorial m plus n plus p upon factorial m factorial n factorial p. Now suppose if we have 2m objects and we have to divide them in a group of m and m, then we can distribute them as factorial 2m factorial n factorial m whole square, and since these two m's are same, we'll divide it by factorial 2. Now suppose we have 2m plus n objects, and we have to divide them in m, m, and n, where m is unequal to n. Then total number of ways of unnamed distributions will be factorial 2m plus n upon factorial m whole square into factorial n, and since these two m's are same, it'll be divided by factorial 2. So we'll be using this in many of the cases wherever we need to form groups or we need to distribute balls into boxes problems. In all those cases, I'll be using unnamed distribution. Right, the question is, in a hotel, 4 rooms are available. So we have 4 rooms, R1, R2, R3 and R4, and there are 6 people, P1, P2, P3, P4, P5 and P6, and they are to be accommodated in these 4 rooms in such a way that each of these rooms contains at least 1 person and at most 2 persons. Now for these 4 rooms, if we assign 1 person each, then we are left with 2 people. Now these 2 people, they are to be assigned in these rooms. Now any room cannot have more than 2 people, so that means they'll be assigned 1 and 1 in 2 rooms. So now we have 2, 2, 1 and 1. So first we'll go for unnamed distribution. So we'll distribute these 6 people. So we'll be factorial 6, factorial 2, 2 times, and then factorial 1. Now since these 2 are same and these 2 are same, so it'll be factorial 2 into factorial 2. Now we have 4 groups. Now we can distribute these 4 groups in these 4 rooms in factorial 4 ways. Now it'll be 4 into 2, 8. So this is 3, and here will be 3 into factorial 5, 120. So which is 120 into 9, it is 1080, and that is the answer to this question. Right, the question is, 4 boys and 4 girls sit in a straight line. Find the number of ways in which they can be seated if 2 girls are together and the other 2 girls are also together but separate from the first 2. Now first what we'll do is, we'll form groups of 2 girls from 4 girls. So we can form this unnamed group in factorial 4 divided by factorial 2, and then since the groups are unnamed, it will be this factorial 2. So now we have 2 groups of 2 girls each. Now we have to separate these 2 groups. For that we'll use gap method. So first we'll arrange these 5 boys. So these 5 boys, they can be arranged in factorial 5 ways. So now we have B1, B2, B3, B4 and B5, and by placing these boys we have created 6 gaps. Now if we have to separate these 2 groups, so we have to arrange these 2 groups in these 6 gaps. So it can be done 6C 2 ways. Now once we have selected 2 gaps, in 2 gaps we can arrange these 2 groups in factorial 2 ways, and in each group we can arrange these 2 girls in factorial 2 ways. So total number of ways will be this factorial 2 will cancel, factorial 4 is 24, factorial 5 is 120, and 6C2 is 15. So it will be 43200, and that is the answer to this question. Today we'll discuss a very interesting problem in permutations and combinations, and the problem is in how many ways we can paint 6 faces of a cube with 6 different colors. So we have 6 different colors and we need to use all the 6 colors, and using all these 6 colors we have to paint all the 6 faces of a cube, and the question is in how many ways can it be done. So the first thing that generally comes to our mind is, now we have 6 colors and 6 faces. So 6 colors on 6 faces can be arranged in factorial 6 ways. So answer to this question is factorial 6. But clearly for this question, answer is not factorial 6. Now how do we solve this problem? To solve this problem, we need to understand linear and circular arrangements. So we'll start with a simple problem. What are the possible arrangements of 3 distinct objects, say A, B and C? So suppose we have 3 distinct objects, A, B and C, and we are discussing their possible linear arrangement. So we know that these 3 objects linearly can be arranged as either ABC,
ACB, BAC, BCA, CAB and CBA. So that is, they can be arranged in 6 ways, which is factorial 3 ways. Now another way of looking at the problem is in terms of number of choices for arrangement. So we have 3 linear positions and they are to be filled with these 3 letters. Now for this first position, we have 3 choices. So it could be any one of A, B or C. Now for the second position, now since one of A, B and C, they have already been positioned. So for the second one, we have 2 choices. And for the last one, we have only 1 choice. So total number of ways in which we can arrange A, B and C in a line is simply 1 into 2 into 3, which is factorial 3 ways, which actually is 6 ways. Pretty simple, right? Now, if we generalize this concept, then if we have n distinct objects and if we have to arrange these n distinct objects linearly, that is, we have to arrange these n distinct objects in n positions, then for this first position, we have n choices. For second one, we'll have n minus 1 choices, then n minus 2 choices, and then simply it'll be 3, 2 and 1. So total number of choices will be 1 into 2 into 3 up to n. So it'll simply be factorial n choices. So the total number of ways of arranging n distinct objects in a line is factorial n. Now, what if we have to arrange ABC on a circle rather than on a line? So now we'll consider circular arrangements. So we have to arrange ABC on a circle. Now on a circle, there are 2 possible arrangements. So either it could be ABC or it could be ACB, and there is no other arrangement possible. So on a circle, we have only 2 arrangements compared to 6 on a line. Now, how do we make sense of this? So what we'll do is, let us try and arrange these 6 linear arrangements on a circle. So we'll make 6 circles. Now first we'll take this ABC. So this is A and then suppose B and then C. First one, it corresponds to ABC. Now second one is ACB. So it is A and then C and then B. So it is ACB. Now BAC. So it is B, then A and then C. So it corresponds to BAC, then BCA. So this is B, C, A. Next one is CAB. So it is C, A, B. And then we have CBA. So it is C, B and A. So which corresponds to CBA. Now if we look at ABC, BCA and CAB, all these 3 arrangements, they are anti-clockwise arrangements of ABC. So basically all these 3 arrangements, they correspond to this one configuration, and that is anti-clockwise arrangement of ABC. Now these remaining 3 configurations, so it is ABC clockwise, it's also ABC clockwise, and here also it is ABC clockwise. So the remaining 3 arrangements, they correspond to this configuration which is ABC in clockwise direction. So all the 6 configurations, basically they give way to only 2 configurations, and which is either ABC clockwise or ABC anti-clockwise. So we have only 2 cases on a circle instead of 6 cases that were present on a line. Now we'll try and figure out why circular arrangements are different from linear arrangements. The difference between a line and a circle is
a line always have a starting point. So suppose when we have a line, we know this line, it starts from here. But when we say we have a circle, so there is no starting point on a circle. So when we arrange n objects in a line, we know that we have a starting point and all these factorial n arrangements, they'll be different. But on a circle, we do not have that luxury of having a starting point. So basically on a circle, what we do is we choose any one object and assign it a place on a circle and then arrange remaining n-1 objects relative to it, and it can be done in factorial n-1 ways. So on a line, n objects can be arranged in factorial n ways, and on a circle, they can be arranged in factorial n-1 way. And that is the reason when we have arranged ABC on a line, we have factorial 3, which is 6 ways, and on a circle, we have factorial 3 minus 1, which is factorial 2, and that is only 2 possible ways. Now we'll come back to our problem, which is we have to color 6 faces of a cube with 6 different colors. Now clearly it is not a linear arrangement, so answer is not factorial 6. All the 6 faces of a cube, they are identical as it was in cyclic permutations. So there is no starting point here as well. So we need to fix one color on any one face and arrange all the other colors relative to it. So out of these 6 colors, we need to paint any one face with any one color. So let us paint one face with, say, red. So let us choose this color red and then we'll paint any one face. So suppose we paint this face with the red. So now we have a starting point on our cube. Now, how many choices we have for the face opposite to this red face? So red, it is already gone. So from the remaining 5, we can put any color on the face which is opposite to this red face. Now we have 5 choices, and from these 5 colors, we can put any one color, say green. So let us put green here. So now we have a cube with 2 opposite faces painted with red and green, and we are left with 4 unpainted faces and 4 colors. So we have 4 faces. So 1, 2, 3 and 4, and then we have 4 colors as well. Now what we'll do is we'll rearrange the cube. So we'll rearrange the cube, then the problem will look little familiar. So what I'll do is I'll rearrange this cube. Now say on the top face we have red color, and then on the bottom face say we have green color. Now we are left with 4 colors and we are left with 4 faces. Now the problem looks familiar. All these 4 faces are similar to arrangement on a circle. So 4 objects on a circle can be arranged in factorial 3 ways. So all these 4 faces, they can be painted in factorial 3 ways. Total number of ways of painting the cube will simply be 5. We have this choice, and then for this circular arrangement, we have factorial 3, which is 5 into 6, and that is 30. So the total number of ways in which we can paint this cube with 6 different colors is 30. Now here the question is, the number of ways in which we can make a garland with 5 flowers of one kind and 3 flowers of another kind is. Now suppose we have 5 A's and 3 B's. Now if we arrange these 3 B's, so we have B, B and B, and we are left with 5 A's. We can distribute these 5 A's as 0, 0, 5, 0, 1, 4, 0, 2, 3, 1, 1, 3, 1, 2, 2, which are total 5 ways. So number of ways of forming this garland is simply 5, and that is the answer to this question. Now question number 20 is, if the word permute is permuted in all possible ways and written in alphabetical order, then 720th word is. So first thing that we'll need to do is we'll need to write these letters in alphabetical order. So we'll get E, E, then M, P, R, T, and U. So we have altogether 7 letters. Now total number of words that starts with E is given by, now we need to arrange these 6 remaining letters. It can be done in factorial 6 ways, and that is 720. So that means this 720th word is actually last word starting with E. Now how do we find last word starting with E? So we'll get this E, and then we have to write all these letters starting from U all the way up to E. So it'll be E, U, T, R, P, M, N, E, and that's your 720th word. So it should be E, U, T, R, P, M, E, and that's your option number B. Now here the question is, an 8-digit number divisible by 9 is to be formed using 8 digits out of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, which are divisible by 9. Now the number of ways in which this can be done is lambda square into 7. We need to find the value of lambda. Now if we look at sum of all these digits, will be n plus 1 by 2, which is 45, which is divisible by 9. Now these are 10 digits. We need to leave out 2 digits such that it still be divisible by 9. So we can leave out 0 and 9. Then we'll have 1, 2 up to 8. Or we can leave out 1 and 8. It'll be 0, 2, 3, 7, 9. We can leave out 2, 7, 3, 6, and 4, 5. So these are the possibilities of leaving these numbers. Now here we have total factorial 8 numbers, which will be 8 into factorial 7. Now in this case, since we have 0 here, number of such numbers will be 7 into factorial 7. Now for each of these 3 cases also, it will be the same. So total number of such numbers will be 8 plus 7 into 4 into factorial 7, which is 28 plus 8, 36 into factorial 7. Now the value of lambda is simply 6, and that is the answer to this question. Now question number 6, it says we have this palindrome. So palindrome is if it reads the same backwards and forwards. Now for example 112211 is a palindrome. So it says how many 6-digit palindromes are divisible by 495. So we will factorize this 495, we'll get 5 into 11 into 9. Now this number will be divisible by 495 when it is divisible by 5, when it is divisible by 11, and when it is divisible by 9. So we have this 6-digit number. Now this number has to be divisible by 5. So that means this number, it should be either 0 or 5. Now it is a palindrome. So that means this digit will be repeated here also. So this cannot be 0. So this last digit, it has to be simply 5. So there is only one choice for this first and last position. Now we have, suppose these two numbers is AB and BA, which makes it a palindrome. Now we look at divisibility by 11. So for divisibility by 11, we look at sum of digits at the even places minus sum of digits at odd places. So what is the sum of digits at even places? So sum of digits at even places is A plus B plus 5. And what is the sum at odd places? So sum at odd will be 5 plus B plus A. So that means sum of even minus sum of odd is simply 0, which is divisible by 11. So this number will be divisible by 11 for any values of A and B. Now we need to find out this number should be divisible by 9. So a number is divisible by 9 if sum of digits are a multiple of 9. So that means 5 plus A plus B plus B plus A plus 5, and it should be some 9k. So I can write 2 times A plus B plus 10, and it should be some multiple of 9. Now we know that this A and B, they belong to this set, which is 0, 1, 2 and up to 9. So what is the minimum value of A plus B? Minimum value of A plus B is 0, and maximum value of A plus B here is 18. Now we need to find all the possible combinations of this sum a plus b so that this 2 times a plus b into 10 is divisible by 9. So this number, it can be 18 and it'll be 18 when we have 2 into 4 plus 10. So one of the possibility is the value of a plus b, it should be 4. So what are the possibilities? Possibilities are 0, 4, 1, 3, 2, 2, 3, 1 and 4 zeros. So that means we have 5 possibilities here. Another one could be when we have this number as 36. It cannot be 27 because here this is 2 and this is 10. Both of them, they are even numbers. So it cannot sum to 27. So if it is 36, then it simply means value of a plus b, it should be 13. Now the other combination that we need to check is when the value of a plus b is 13. So what are the possible combinations? So possible combinations are 4, 9, 5, 8, 6, 7, 7, 6, 8, 5 and 9, 4. So these are the possible configurations where the sum a plus b into 2 plus 10 is a multiple of 9. So which is 5 and then 6, 11 cases. So the total number of 6-digit palindromes which are divisible by 495 is simply 11. That's your option number B.
Now here the question is, we need to find sum of all the numbers that can be formed using all the digits 2, 3, 3, 4, 4, 4. Now what we'll do is, first we'll find sum of digits at any one particular place, say units place. So for that what we'll do is, we'll find number of numbers which will have 2 in the units place. So if 2 is there, then number of such numbers will be factorial 5 divided by factorial 2 factorial 3, which is simply 10. Now numbers ending with 3. Now here we'll have factorial 5 divided by factorial 3, that is 20. And numbers ending with 4 will be factorial 5 divided by factorial 2 and it will be 30. So we find sum of digits at units place will be 2 into 10 plus 3 into 20 plus 4 into 30 and it will be 20 plus 60 plus 120 and that is nothing but 200. Now using symmetry we can say sum of digits in units place is equal to sum of digits in tens place, hundreds place. So sum of all these numbers will be this 200 into units place, tens place, hundreds place, thousands place plus 100,000 place. So it will be 111 into 200, which is 222,222,00, and that's your option A. Right, the question is, how many 4-digit numbers are there which contains not more than 2 different digits? Now, first possibility is, suppose the numbers are formed from 1 digit only, and it will be 1111, 2222 up to 9999, and there will be 9 such numbers. Now the second possibility is that the numbers contains exactly 2 digits. Now we consider 2 separate cases. Case 1, if the 2 numbers they are unequal to 0, and case 2, when one of the number is 0. Now if 2 numbers are not 0, we can select these 2 numbers in 9C2 ways. Now with A and B we can have arrangements with A and 3 B's, or 2 A's and 2 B's, or 1 B and 3 A's. Now total number of numbers that can be formed is 9C2 and it'll be all the numbers that can be formed with A and B, and it'll be 2 into 2 into 2 4 times, minus 2 cases where we have either all A's or all B's. So it'll be 36 into 14 and it'll be 504. Now we consider all the numbers which contains A and 0. Now we can select this A in 9C one ways, and then we have the numbers as AAAO or AA00 or A000. Right here, number of numbers that can be formed is 9C1. Now here we can have the 0 in 3 positions, so it will be 3 such numbers, plus here also this A will be fixed and these A00 will be arranged in 3 ways, and plus 1, so it will be 9 into 7, which is 63. So total number of such numbers will be 9 plus 504 plus 63, and which is 576. So there will be 576 4-digit numbers which contains not more than 2 different digits. Now the question is, how many divisors are there of the number x equals 21600? Now we can write this x as 2 to the power 5, 3 to the power 3 into 5 square. Then number of divisors, it is given by a plus 1, so it will be 5 plus 1 into b plus 1, 3 plus 1 into c plus 1, which is 2 plus 1. So it will be 6 into 4 into 3, and there will be 72. So there will be 72 divisors of this number. Now next is we need to find sum of these divisors. Now we know that sum of these divisors is given by 1 plus 2 up to 2 to the power 5, 1 plus 3 up to 3 cube, and then 1 plus 5 plus 5 square. Now this is 2 to the power of 6 minus 1. It is 3 to the power of 4 minus 1 divided by 2 into, this is 25 plus 5, 30, 30 plus 1 is 31. So it will be 78120. So sum of all these divisors will be 78120, and that's your part A. Now part B is, we need to find number of ways in which 7056 can be resolved into product of 2 factors. Now we can write this 7056 as 2 to the power 4 into 3 square into 7 square. Now since this n is a perfect square, then number of ways in which we can resolve this number in a product of 2 factors will be given by 1 by 2 into, now a plus 1 5, b plus 1 3, c plus 1 3, and then plus 1. So it will be 45 plus 1 46, 46 divided by 2 is 23. There will be 23 ways in which we can resolve them as a product of 2 factors. Now this C is, we have to find number of ways in which this number 300 can be split into 2 prime factors. Now we can write this as 3 into 5 square into 2 square into 7 into 11 into 13. Now there are 6 distinct primes in this. The number of ways of distributing this n into 2 relatively prime or co-prime factors is given by 2 to the power of p minus 1, where p is number of distinct primes. Now in this case, number of distinct primes is 6, so it will be 2 to the power of 6 minus 1, and there will be 32 ways.
Now this is famous 1000 doors problem, and this problem we have already discussed in one of the previous videos. So there I have discussed this problem in detail. Here I'm just going to skim through it. So we have 1000 doors, D1, D2, D3 and D1000, and there are 1000 people, P1, P2, P3 and P1000. Initially all the doors are closed. P1 opens all the doors, P2 closes all the doors which are multiple of 2, P3 changes the status of all the doors which are multiple of 3, and it goes on. So the question is, until lastly P1000 changes the status of D1000, then which of the following options are correct? So we have to find number of doors which are open. Now we know that any door will only be touched by a person whose number is one of the divisors of the door number. Say door number 6 will be touched by P1, P2, P3 and P6. So any door can only be touched by a person whose number is a divisor of the door number. Now we need to find how many doors will be open. So a door, it will be open when it is touched by odd number of people. So it will be touched by odd number of people if the number has odd number of divisors. So all the doors which are open will have the number which have odd number of divisors. Now we know that for any number n whose prime factorization is p1 to the power a1, p2 to the power a2 and pk to the power ak, number of divisors is given by a1 plus 1, a2 plus 1 and ak plus 1, and this number, it will be odd when each of a1, a2 and ak, they are even. And if they are even, then all the powers, they are even powers. That means this n, it must be a perfect square. So all the doors whose number is a perfect square of some number, they'll be open, and all other doors, they'll be closed. So such doors are 1 square, 2 square, 3 square, and then 30 square is 900, and then 31 square, which is 961. So overall, there'll be 31 doors which are open. So number of doors which are open is 31, and that's your option A. Now, greatest number of consecutive doors that are closed finally. Now, this greatest number is between this door number 900 and door number 961, and there are 60 such numbers. So that means this option B is also correct. Option C is the door having greatest number that is finally open is D961. It is also true. And D is greatest number of consecutive doors that are finally closed is 61. No, this is not 61, it is 60. So this option D is incorrect. So the correct options are A, B and C.
Now here the question is, if R, S and T are prime numbers and P and Q are positive integers such that LCM of PQ, it is R square T to the power 4 into S square, then number of ordered pairs of PQ is. Now we have two numbers P and Q, and their LCM is R square T to the power 4 into S square. Now if we look at R square, and since LCM is R square, so one of P or Q, it must contain R square. Then possibilities for Q are 1R and R square, and it could be R square in Q, and then P could be 1R and R square. Now this R square, it is covered in both the cases. So total number of ways of distributing this R is simply 5. Now for T to the power 4, if we have T to the power 4 here, it will be 1T, T square, T cube and T to the power 4. And if T to the power 4 is here, possibilities are 1T, T square, T cube and T to the power 4 and T to the power 4. Now T to the power 4, again this case is covered in all the cases, so it will be 5 plus 4, 9. So there will be 9 ways of distributing this T. And S square, it is same as R square, so there will be 5 ways for S square. So total number of ordered pairs of P and Q will be 5 into 9 into 5, and it is 225. That's your option C.
Now here the question is, let Sn be set of all n-digit numbers. The numbers of numbers in S6 consisting of digits 0, 3 and 5 only, with each of them appearing at least once is. Now we'll solve this question using inclusion, exclusion. So first we'll find total number of 6-digit numbers that can be formed using these 3 digits. So it is a 6-digit number. Now for this first place, we have 2 choices. It can be either 3 or 5. So we have 2 choices here. And for these remaining 5 places, it will be 3 choices each. So we can write this as 2 into 3 to the power 5, which is 486. Now from these total numbers, we'll remove all the cases where at least one of these 3 digits is missing. So first we'll find all the cases in which at least one is missing. Now this missing digit, it could be 0 or 3 or 5. Now if the missing digit is 0, then total number of numbers that can be formed is simply 2 to the power 6. Now if the missing number is 3, for the first place we have only one option. And for remaining 5 we have 2 options each. In the same way for 5 also, it will be 2 to the power 5. So this is 2 to the power 7 and that is 128. Now from this we'll subtract all those cases where 2 of them they are missing, because we know that n A union B union C is NA plus NB plus NC minus NA intersection B, B intersection C and C intersection A. Now if 1 and 3 they are missing, it will be this one case, all the numbers formed with 5, minus if 0 and 5 are missing, again one case, and if 3 and 5 are missing, and if both 3 and 5 are missing, it will be simply 0. So there will be no other case. So it will be 126. So there are 126 cases in which at least one of 0, 3 and 5 they are missing. So total number of cases or total number of numbers in which all these digits they appear at least once, it is given by 486 minus 126, which is 0, 6 and 3. So it will be 360 and that's your option A. Now the next question is the number of numbers in S6 having exactly 3 different digits. Now these 3 different digits they may have 0. So it could be 0 and then any 2 digits A and B, or it can be all 3 non-zero digits A, B and C. Now if one of the digit is 0, then we have to select these 2 digits and it can be done in 9C 2 ways. Now once we have 0, A and B, this case it is similar to this first case when we have 0, 3 and 5. In this case, total number of numbers which have each digit at least once, it is 360. So it will be 9C2 into 360 plus, now all these 3 numbers they are non-zero. So it will be 9C3, and from these 3 numbers, total number of numbers that can be formed which have all the digits at least once, it will be given by this inclusion exclusion. So for this 6-digit number, for each place we have 3 options. So it will be 3 to the power 6 minus at least 1 is missing. So it is 3C1 to the power 6 minus 2 are missing, 3C2 1 to the power 6. So this value will be 36 into 360 plus 9C3. 9C3 is 987 and this is 3 into 2. So this is 3, 4, 12. 12 into 7 is 84. Now 3 to the power 6 is 729 minus this is 3 into 2 to the power 6, which is 64 and plus 3. And this value it is equal to 58320, and that's your option B. Now here the question is, a party of 10 consists of 2 Americans, 2 British, 2 Chinese and 4 men of other nationalities, all different. Find the number of ways in which they can stand in a row so that no 2 men of same nationality are next to each other. Now we'll solve this question using inclusion exclusion. Now total number of ways of arranging these 10 people, it is simply factorial 10. Now from this factorial 10 we'll subtract all those cases where at least 2 people from same nationality are together. So it is given by 3C1. It could be either Americans or British or Chinese, and if these 2 are together we can use string method. So there will be 4 plus 8 and 1 9. So there will be factorial 9 ways, and then these 2 they can be arranged in factorial 2 ways. Minus, now we'll subtract all those cases where people of 2 nationalities are standing together. So 2 out of 3 it can be selected in 3C2 ways. Now suppose there are 2 Americans and 2 British. So again we'll use string method. So now we have 1, 2 and 6, 8. 8 objects which can be arranged in factorial 8, and these 2 among themselves they can be arranged in factorial 2 and factorial 2 ways. Now plus when all the 3 are standing together. Now we have 7 objects, they can be arranged in factorial 7 ways, and then it will be factorial 2, factorial 2 and factorial 2. So it will be this factorial 10 minus, now this is 3 into 2 6 into factorial 9 minus this is 3 into 4 12 into factorial 8 plus 8 into factorial 7, which is factorial 8. Now what we'll do is we'll take factorial 8 common. So if we take factorial 8 common, it'll be 90 minus 54 plus 12 minus 1, and it'll be 47 into factorial 8. So total number of ways in which they can stand in a row so that no two men of same nationality are together, it is given by 47 into factorial 8. Now we have to find number of ways in which they can sit at a round table. At a round table, the total number of ways in which they can be arranged is factorial 9 and then minus. Now when suppose two Americans are together, so it could be either 2 Americans, 2 British or 2 Chinese. So it will be 3C1, and if they are together, we have 9 objects which can be arranged in factorial 8 ways, and then it will be factorial 2 minus 3C2, and suppose there are 2 Americans and 2 British now. So now we have 8 items which can be arranged in factorial 7 ways in a circle, and then it will be factorial 2, and then plus all the 3 are together. So it will be factorial 6 into factorial 2, and factorial 2. Now we'll take factorial 6 common. So if we take factorial 6 common, it will be, now here will be 9 into 8 into 7, and then minus this is 3 into 8 into 7 into 2 plus 3 into 7 into 4, and then minus 8, and it will be 244 into factorial 6. So they can be arranged in a circle so that no two men of same nationality are together. It will be 244 into factorial 6.
Another method to prove derangement formula is using inclusion-exclusion method. Now before getting on with this method, so I'll describe the situation, and the situation is there are n people P1, P2, P3 and Pn, and then there are n houses H1, H2, H3 and Hn, and each person has his or her own assigned house. So this house H1 belongs to P1, H2 belongs to P2, H3 belongs to P3 and Hn belongs to Pn. Now we want to work out the total number of dearrangements so that none of the person goes to his or her assigned house. For this inclusion-exclusion method proof, I'll define n events and I'll define them as A1, A2, A3 and then An. Now A1 event defines the condition when P1 goes to his or her own house H1. Similarly, A2 defines the condition when person 2 goes to H2, person 3 goes to H3, and An is person n goes to his or her own house Hn. Now I'll need to work out total number of ways in which these person can be arranged or assigned these houses so that no person goes to his or her own house. So now I'll need to find Dn. So now in order to find the dearrangement of these n people, what I'll do is I'll take up total number of arrangements and from all these arrangements I'll subtract all those cases where at least one of the person goes to his or her own house. So that is, I need to subtract all those cases where at least one of P1, P2, P3 or Pn goes to his assigned place. So that is, I need to find number of cases when at least one of A1, A2, A3 and An has occurred. Now the total number of arrangements is, so we have n houses and n people. So these n people can be arranged in n houses in factorial n ways. So there will be factorial n and then minus. Now what is n A1 union A2 union A3 union An? So this formula is simply nothing but summation n Ai minus summation n Ai intersection aj, and then plus summation n ai intersection aj intersection ak, and this condition will continue up to summation n ai intersection aj, and then for all the n people, that is a1, a2n, an, and then it will be minus 1 to the power n minus 1. So I'll write it as factorial n minus, now what is this condition na1? So the condition is when this person 1 goes to his or her own house. So if person p1 is assigned to the house h1, then the total number of ways in which the remaining n minus 1 people can be assigned or can be arranged in these remaining n minus 1 houses is factorial n minus 1. Now how many terms do we have in this summation? So in this summation we have a term for a1, then for a2, for a3, for an. So we'll have n terms. Another way of doing it can be I have to select only one person, and this one person can be selected in nc1 ways. So I can write nc1 into factorial n minus 1. Now for two people, now suppose if p1 and p2 they are in assigned place, then remaining n minus 2 people they can be arranged in factorial n minus 2 into, now in how many ways can I select two distinct people? It can be done in nc2 ways, and then plus n minus 3 factorial into nc3, and it will continue up to minus 1 to the power n minus 1, and then if all the people they are in their assigned position, then in that case there will be simply 1. So I'll get factorial n minus factorial n minus 1, and nc1 is simply n by 1. It will be factorial n minus 2, and this is n minus 1 upon factorial 2. Here it is n minus 3 factorial, and then n minus 1, n minus 2 upon factorial 3, and finally it will be minus 1 to the power n minus 1, and this is factorial n upon factorial n. Now what I can do is I can write factorial n minus 1 into n as factorial n minus 1 factorial n minus 2 is also factorial n. This value is also factorial n, and this is again factorial n. So I can write it as factorial n minus factorial n upon factorial 1 minus factorial n upon factorial 2 plus factorial n upon factorial 3, and will continue up to minus 1 to the power n minus 1 factorial n upon factorial n. So now I'll take factorial n common. So if I'll take factorial n common, then I can get 1 minus 1 upon factorial 1 plus 1 upon factorial 2 minus 1 upon factorial 3, and will continue up to, then here will be minus and minus, so it will be minus 1 to the power n into 1 upon factorial n, and which is dn. So that is the formula proof for dn, which is dearrangement of n object, and I can also write it as dn as factorial n and then summation k varies from 0 to n minus 1 to the power k upon factorial k. This is how we prove this formula.
Now here the questions. The number of ways in which 4 married couples can be seated such that 4 persons are on left side and 4 are on right side on a long table, and no wife is in front of her husband, and same gender person do not sit opposite to each other. Now we have 4 husbands, H1, H2, H3 and H4, and we have 4 wives, W1, W2, W3 and W4. Now first we have to match them in pairs so that we get a man and a woman in a pair, and husband should not be matched to wife. Now this is nothing but derangement, and it is D4, and D4 is 9. So once we have this derangement, now we have 4 pairs of husband and wife which are to be arranged along a long table. Now along a long table, these 4 pairs, they can be arranged in factorial 4 ways. Now in each pair, the 2 people, they can be arranged in factorial 2 ways. So it will be factorial 2 into factorial 2 into factorial 2 4 times, and that will be factorial 2 to the power 4. So this is 9, factorial 4 is 24, and this is 16, and which is 144 into factorial 4, and that's your option A. Now here the question is, there are 6 cards and 6 envelopes. So let the cards be C1, C2, C3, C4, C5 and C6, and we have 6 envelopes: E1, E2, E3, E4, E5 and E6. Now they are to be placed in envelopes so that each envelope contains exactly 1 card and no card is placed in the envelope bearing the same number, and moreover the card number 1 is always placed in envelope number 2. So this card number 1, it is always placed in envelope number 2. Now we have 2 cases. Case 1, when card number 2 is also placed in E1, then in that case it is equal to D4, which is derangement of 4 objects. Or this second case, when C2, it doesn't go to E1. Now if C2 doesn't go to E1, then it is nothing but derangement of 5 objects. So it will be nothing but D5. Now D4 is 9 and D5 is 44. So 9 plus 44 is simply 53, and that's your option C. In this video, we'll be discussing how to find number of relations defined on A cross A. Now before that, my basic assumption is, we already know that if we have a set A having n elements and set B having m elements, then number of elements in A cross B is given by m into n. And also we know that total number of relations defined on A cross B is given by 2 to the power of mn. A relation is nothing but a subset of A cross B. So total number of subsets of A cross B will be 2 to the power of mn. Now we'll start finding number of relations defined on A cross A. So first we'll find total number of relations defined on A cross A. Now number of elements in A cross A is given by n square. So total number of relations is given by 2 to the power of n square. So total number of relations that can be defined on A cross A is simply 2 to the power of n square. Now we know that number of elements in A cross A will be n square. So suppose we express this A cross A with this matrix, which is A1, A2, A3 and AN, and here it will be A1, A2, A3, and then again we have AN. So we have n rows and n columns. So altogether we have total n cross n, that is n square elements. Now elements in the diagonal, they are A1, A1, A2, A2 and AN, AN. Non-diagonal elements are A1 R A2 and this is A2 R A1. Now how many diagonal elements are there? So are these n square elements? Total number of diagonal elements is simply n. Then number of non-diagonal elements will be n square and then minus n, which is number of diagonal elements. So we have total n square elements, out of which n elements are diagonal elements and remaining elements are n square minus n elements. Now we'll find number of reflexive relations on A cross A. Now we know that a relation is reflexive when each element is related to itself. So that means for this relation to be reflexive, all these diagonal elements, they must be present in the relation. So it must have A1, A1, A2, A2 and AN, AN. So we have already selected these n elements. Now for each of the remaining non-diagonal element, we have two choices. Either we can select that element in the relation or we may not select it. So for first element, we have two choices.
For second element, we have two choices. So for all the non-diagonal elements, we'll have two choices each. So it'll be 2 into 2 into 2, n square minus n times. So number of reflexive relations in A cross A will be 2 to the power n square minus n. Now third, we'll find number of symmetric relations. Now a relation is symmetric if A comma B is in the relation, then it implies that B comma A must also be included in the relation. Now for diagonal elements, we do not have any problem. If we include A comma A, then it's symmetric relation. A comma A, it is already there. So for each of these n elements, we have two choices each. So it'll be 2 to the power n. Now what about non-diagonal elements? Now for non-diagonal elements, if we select any element, then we have to select its corresponding symmetric elements. So what we'll do is we'll find number of elements in lower triangular matrix. Now out of these n square minus n square minus n by 2 elements will be below the diagonal, and n square minus n by 2 elements will be above the diagonal. So for each of these n square minus n by 2 elements, we have two choices. Either we'll include it or we won't include it. So total number of choices for these elements will be 2 to the power of n square minus n by 2. Now once we have selected any element, then its symmetric element will be included. It will be 2 to the power of n square plus n by 2. So number of symmetric relations is 2 to the power of n square plus n divided by 2. Now the fourth one is number of anti-symmetric relation. A relation is anti-symmetric if A comma B is included in the relation, then B comma A is not included if A is unequal to B. Now for anti-symmetric relation, we again don't have a problem with these diagonal elements. So for each of these n diagonal elements, total number of ways in which we can select them is 2 to the power n. Now for these non-diagonal elements, we have n square minus n by 2 pairs. We are considering A2 A1 and A1 A2 as pairs. Now for each pair we have 4 choices, 2 for A1 A2 and 2 for A2 A1. Out of these 4 choices, we have to eliminate the choice when we have selected both of them, because if we have selected both of them, then it won't be an anti-symmetric relation. So that means out of these 4, we have to select 3 choices for each of the pair. So it'll be simply 3 and then 3 into 3 into 3 for total n square minus n by 2 pairs. So total number of anti-symmetric relations will be 3 to the power n square minus n by 2. Now the fifth one is number of transitive relations. Now unfortunately there is no closed form for transitive relations, but in one of the research papers they have tried to define number of transitive relations in terms of successive summations as recurring relation. I'll provide the link to that research paper in the description below. As of now, we'll say there is no closed form for number of transitive relations. Now we'll come to number of equivalence relation. So here we need to find number of equivalence relation defined on A cross A. Now we know that equivalence relation partitions the set into equivalence classes, and which is equivalent to counting the number of partitions of any given number n. So number of equivalence relation on A cross A is defined by number of partition of A into subsets. Now this number of partitions is given by Bell number, and we denote it by Bn. So total number of equivalence relations on A cross A will be equal to Bn. Now here B0 is 1, B1 is 1, B2 is 2, B3 is 5. Now if we have to find any higher Bell number, then it is given by this recurring relation, which is Bn plus 1, and it is equal to this summation. K varies from 0 to n, nck and bk. So all we need to do is we need to just memorize first few terms, and then we can use this summation to write any Bell number to find total number of partitions, which is equivalent to number of equivalence relation defined on A cross A. Now suppose we have to find B4. Now B4 will be this summation. K varies from 0 to 3, 3ck and bk. So it'll be 3c0b0 plus 3c1b1 3c2b2 plus 3c3 into b3. Now 3c0 is 1 and b0 it is also 1. 3c1 is 3, b1 is 1, 3c2 is 3 and b2 is 2, 3c3 is 1 and b3 is 5. So it'll be 5 plus 6 11, 11 plus 4 15. So value of b4 is 15. So fourth Bell number is 15. So number of equivalence relation on A cross A, if number of elements in A is 4, is 15. So this is how we find number of equivalence relation on A cross A.
In permutations and combinations, we generally discuss questions such as find the number of relations from A to B, or number of functions, number of one-on functions, or maybe number of onto functions. Now here we want to discuss, or we want to derive a general formula for number of onto functions from a discrete set A to a discrete set B, where number of elements in set A is n and number of elements in set B is m. And clearly this n, it has to be less than or equal to n. Now in case, suppose m is greater than n. Now let us take an example. Say I have two elements A1 and A2, and suppose here the value of n is 2, and suppose m is greater than n. Suppose m is 3. Suppose I'll take this as B1, B2 and B3. Now for this function to exist from A to B, A1 must have an image. So maybe A1 has an image B1. A2, suppose it has an image B3. Now there will always be at least one element which will not have any pre-image. So in this case, it cannot be an onto function. So in this case, number of onto functions will simply be 0. So if n is greater than n, then in that case, simply I'll say number of onto functions will be simply 0. So we want to work out a general formula when this m is actually less than or equal to n. Now, one of the way of doing it is, first I'll find total number of functions. Total number of functions that can be defined from A to B. Now, in order to define total number of functions, what I need is, for this A1, there must be an image. So it can be either B1, B2 and Bn. So there are m choices, and out of these m choices, I'll just need to select any one choice of image for A1. So in how many ways can it be done? It can be done in m ways. Again for A2, there are m choices. Again m for A3, and then finally it will be again m for An. So if I look at all the choices for all the elements, then it comes to m to the power n. So total number of functions from A to B that can be defined as m to the power n, where n is number of elements in this set A and m is number of elements in this set B. Now we'll find out total number of into functions from A to B. Now how do we work out number of into functions from A to B? Now for that we have to look into the definition of into function. A function is an into function if at least one the element in set B doesn't have a pre-image. So that means I'll have this condition where at least one of this Bi doesn't have a pre-image. Now how do I find that? So I'll say I need to find number of functions defined from A to B so that at least one of B1, B2, B3 or Bn, it should be missing. So here when I say B1, so it means the element B1 is missing. It doesn't have a pre-image. B2, element B2 doesn't have a pre-image. So at least one of these elements, it should not have a pre-image. Now we know that this formula can be generalized as summation n B1 minus summation n B1 intersection B2 plus summation n B1 intersection B2 intersection B3. So we can generalize this formula. Now how many functions can be defined from A to B so that B1 doesn't have a pre-image? So that is how many functions can be defined from A to B so that B1 doesn't appear in the range. So these each of these elements A1, A2 and AN must find an image from B2 to Bm. So for A1, we have m-1 choices. For A2 again, I'll have m-1 choices. And for An again, I'll have m-1 choices. So the total number of functions that can be defined from A to B, which doesn't include B1, is simply m-1 to the power n. Now, same is the case with B2. For B2 also, I'll get this n-1 c to the power n. For Bm also, m-1 to the power n. So that is, I'll have the same condition for each of B1, B2 and Bn. So in order to find this summation, so in how many ways can I select single element? So it can be done in MC1 ways. So this summation nB1 is MC1 into m-1 to the power n. Now what about B1 intersection B2? So it simply means that B1 is missing and B2 is also missing. Now in this case, the total number of choices for A1 is simply m-2. For A2 also, it will be m-2. So it will be m-2 to the power n, because for each A1, A2 and An, I have m-2 choices. And then now in how many ways can I select a combination of two elements? So it can be done in, from m elements, I'll just need to select two elements, and that can be done in MC2 ways. For the third one, I think it should be plus MC3 m-3 to the power n, and this series will continue. So this is how we can find out total number of into functions from A to B. So I can find out number of onto functions as total number of functions, which is simply m to the power n, and then minus total number of into functions, which is minus mc1 m-1 to the power n minus mc2 m-2 to the power n plus mc3 m-3 to the power n, and will continue. So I can in fact write it as n to the power n minus mc1 m-1 to the power n plus mc2 m-2 to the power n minus mc3 m-3 to the power n. So I can write it as mc0, mc1, mc2. So it will be mcr and then minus 1 to the power r. So when r is even, it should be plus, and when r is odd, it should be minus, and then it should be m minus r to the power n, where this value of r varies from 0 to m minus 1. The number of onto functions that can be defined from set A to set B, where A has n elements and B has m elements, is given by this formula, which is summation r varies from 0 to m minus 1, mcr minus 1 to the power r, m minus r to the power n. So let us take up an example. Suppose I have to find number of onto functions defined from set A to B, so that number of elements in set A is 4 and number of elements in set B is 2. So in this case, the value of n is 4 and the value of m is 2. So clearly n is greater than m, so I can use the formula. Now the formula is number of onto functions is given as summation r varies from 0 to m minus 1, and m minus 1 in this case will be simply 1, and there will be m, so which is 2cr minus 1 to the power r, and which is 2 minus r to the power n, and n in this case is 4. Now if I'll put r as 0, I'll get 2c0 minus 1 to the power 0, 2 minus 0 to the power 4, and then plus 2c1 minus 1 to the power 1, and will be 2 minus 1 to the power 4. So here it will be 2 to the power 4, which is 16, and then it will be minus 2c1. So there will be 16 minus 2, that is 14. So number of onto functions from set A to set B, when number of elements in set A is 4 and number of elements in set B is 2, is simply 14.
Today in permutations and combinations, we'll be discussing problems on number of functions defined from A to B. So in this video, we'll be studying number of elements in A cross B, number of relations defined on A cross B, number of functions that can be defined on A cross B. Then we'll find a general formula for number of one-one functions and many-one functions, number of into functions and onto functions, number of bijective functions, then number of bijective functions with derangement condition, then we'll find number of strictly increasing or strictly decreasing functions, and in the end we'll find number of non-decreasing or non-increasing functions. Now in many cases, number of functions problem is directly related to number of ways of distributing balls and boxes problem. So if we have distinct balls and distinct boxes, then that problem can be mapped to number of functions defined from set A to set B. So here elements in set A will correspond to distinct balls, and elements in set B, they'll correspond to distinct boxes. Now we'll start with number of elements in A cross B. Now we know that A cross B is nothing but an ordered pair A comma B, where A belongs to the set A and B belongs to the set B. Now suppose number of elements in A is n and number of elements in B is m. Then what are the total number of ways of choosing A? So total number of ways of choosing A is n and total number of ways of choosing B is m. So total number of elements in A cross B is simply m into n. So number of elements in A cross B is mn. Now what about number of relations defined on A cross B? Now we know that any relation is nothing but a subset of A cross B. So how many subsets of A cross B are possible? Number of subsets of A cross B will be 2 to the power of mn. So number of relations that can be defined on A cross B is 2 to the power mn. Now in one of the previous videos, we have already discussed how to find number of relations defined on A cross A, and with that how to find number of reflexive, symmetric, antisymmetric, transitive and equivalence relation. So I'll provide the link to that video in the description below. Now what about functions on A cross B? Now we have the set A, and this set A has n elements, say A1, A2 and An, and then we have the set B which has m elements, say B1, B2 and Bm. Now any relation is a function if for each and every element in domain A there exists an image in set B and that image is unique. So that means for this element A1 we need to find an image in the set B. So how many choices do we have for this element A1? So for this element A1 we have m choices. So it can be mapped to either B1 or B2 or B3 or Bm. And the same way for A2 we again have m choices. For A3 again we'll have m choices. So it'll continue for all the n elements. So total number of functions from A to B will be m into m into m up to n times. So there'll be total m to the power n functions. So total number of functions defined on A cross B will be m to the power n, where n is number of elements in set A and m is number of elements in set B. Now we need to find number of 1, 1 functions. Now a function will be 1, 1 if for 1x there is 1y and for 1y there is only 1x. So that means for these n elements we have to choose n elements in B which are going to be mapped uniquely to each of these elements A1, A2 and An. Now for a function to be 1, 1 function, value of m, it must be greater than or equal to n. Because if the value of m is less than n, then from PHP, which is pigeonhole principle, we can say that at least two elements will have the same image. So if m is less than n, then number of 1, 1 functions will be 0. All the functions will be many 1 functions. And if m is greater than or equal to n, then what we'll do is from these m elements, we'll have to select first n elements. So m from n, they can be selected in MC n ways. Now we have n A1s and we have n elements in B. Now these n elements, they have to be uniquely mapped to n elements in B. Now one way of looking at the problem is this is nothing but permutation of n elements of A with n elements of B, and it can be done in factorial n ways. So number of 1, 1 functions, it will be MPN. So number of unknown functions is mpn provided m is greater than or equal to n. If m is less than n, then in that case number of unknown functions will be simply 0. Now what about number of many known functions? To find number of many known functions, all we simply need to do is we'll take total number of functions, so that is m to the power n, and then from total number of functions we'll exclude all the one-known functions. So number of many known functions will be m to the power n minus mpn. Now we'll come to number of into n onto function. We know that a function will be an onto function if codomain is equal to its range. So that means each and every element in this set B must have a pre-image. In balls and boxes problem, this question corresponds to number of ways of distributing n distinct balls in n distinct boxes so that none of the box is empty. So here we need to find number of into functions and number of onto functions. Now in one of the previous videos, we have already discussed how to work out a formula for number of into functions and number of onto functions. In that video, we have discussed in detail how to work out formula for number of into functions and number of onto functions. So I'll provide the link to that video in the description below, so you can follow the proof of the formula. Here, I'm just going to write the formula. So formula for number of into functions is summation r varies from 1 to m minus 1 to the power r plus 1 mcr into m minus r to the power n. So number of into functions defined from a to b, where number of elements in A is n and number of elements inside B is m, is given by summation r varies from 1 to m minus 1 to the power r plus 1 mcr m minus r to the power n. And if we have to find number of onto functions, then number of onto functions is given by r varies from 0 to m minus 1 to the power r mcr m minus r to the power n. We can also write number of onto functions as factorial n into SNR, where SNR is Stirling's number of second kind. Now we'll come to number of bijective functions. Now we know that a function will be bijective if it is both 1, 1 and onto. So function can only be a bijective function when m is equal to n. That is, number of elements in A is same as number of elements in B. If number of elements in A is not equal to number of elements in B, then in that case, number of bijective functions will simply be 0. Now when m is equal to n, then we have n elements in set A and n elements in set B. All we need to do is we need to assign one-to-one correspondence between the elements. So it is nothing but again permutation of n objects. So number of bijective functions defined from A to B if m equals to n will simply be factorial n. Now there have been some questions where they may use the derangement condition. So what they'll say is they'll say a function f is defined from A to A, where A is this set 1, 2, 3 up to n. Then how many bijective functions can be defined, or how many one-one functions can be defined from A to A such that fi is unequal to I. So in the question, 1 should not be mapped to 1, 2 should not be mapped to 2, and n should not be mapped to n, and it has to be a bijective function. This condition is clearly nothing but this condition is condition of derangement. So that means we need to arrange these n objects in n places so that no object goes to its assigned place. So it is nothing but dn. So number of such functions will be given by this dn. dn is nothing but factorial n and then 1 minus 1 upon factorial 1 plus 1 upon factorial 2 minus 1 upon factorial 3, and will continue up to minus 1 to the power n factorial n. Now in balls and boxes problem, suppose we have n colored balls and n colored boxes. Now in how many ways can we distribute these n balls in n boxes so that each box has exactly one ball and no ball goes to its same color box. So again, this is derangement, which is dn. Now we'll come to number of strictly increasing and strictly decreasing functions. Now suppose we have the set A containing n elements, and we have the set B containing m elements, and we need to find number of strictly increasing functions defined from A to B. So question will be given, f is defined from A to B, and we need to find number of functions such that fx is less than fy if x is less than y, or they'll say this function is strictly increasing function. Now if it is strictly increasing function, we know that this function has to be a 1-1 function. So that means for each of these elements in set A, we must have corresponding n elements in set B. So this condition is only possible when the value of m is greater than or equal to n. If the value of m is less than n, in that case, there cannot be strictly increasing function. So if m is greater than or equal to n, then for these n elements, we'll select n elements from set B. N elements from set B, it can be selected in MC n ways. So now we have n elements on the left and we have n elements on the right. Now we have to map each element in such a way that it becomes an increasing function. So for A1, A2, A3 and AN, we have to permute this B in an ascending order. Now in how many ways we can arrange n numbers in B in ascending order? Distinct numbers can be arranged in ascending order in only one way. So number of strictly increasing, or for that matter number of strictly decreasing functions defined from A to B will be simply MCN. So if the problem is find number of strictly increasing or strictly decreasing function, then the value of m has to be greater than or equal to n. And if the value of m is less than n, then number of such functions will be 0. And if m is greater than or equal to n, in that case number of strictly increasing or strictly decreasing function will simply be MCN. Now we'll find number of strictly increasing and strictly decreasing functions defined from set A to set B. So we have this function f defined from set A to set B. Suppose set A has n elements, and say the elements are A1, A2, A3 and AN, and set B, it has m elements, which are B1, B2 and Bm. Number of elements in set A, it is n, and number of elements in set B is m. Now we need to find number of strictly increasing functions defined from A to B. Now in order to define strictly increasing functions, the elements in set A, they must be arranged in some order. So what we'll do is we'll assume that the elements in A are such that A1 is less than A2, is less than A3, and it is less than AN. So for simplicity, we have assumed that this set A is an ordered set in which A1 is the smallest element and AN is the largest element. And by doing so, we have not changed the question. We have rearranged the elements in the set. So the question will either be find number of strictly increasing functions from A to B, or they may ask you to find number of functions from A to B such that FAI is less than FAJ whenever I is less than J. Now we know that any strictly increasing function is a 1-1 function. So this function from A to B, it has to be a 1-1 function, and it can only be a 1-1 function when the value of m, it is greater than or equal to n. Now if m is less than n, in that case there will be no 1-1 function possible. So their number of strictly increasing or decreasing function will simply be 0. Now we'll consider this general case when m is greater than or equal to n. Now since it is a 1-1 function, from these m elements, we have to select n elements so that we can get image for each element. Now n elements from m can be selected in MC n ways. So now we have n elements in A and we have n elements in B. Now we have to map each element in A with an element in B so that FAI is less than FAJ. That means selected n numbers in set B must be mapped with elements in A in an ascending order. Now, in how many ways we can arrange n distinct elements in ascending order? There is only one way possible. So, number of strictly increasing function, or for that matter, number of strictly decreasing function also from set A to set B is given by MCN whenever m is greater than or equal to n. And if m is less than n, number of such functions will be simply 0. The problem becomes little more interesting when it says number of non-increasing or non-decreasing functions defined from set A to set B. So suppose again we have set A in which elements are ordered, say A1 is less than A2 is less than A3 is less than AN, and suppose now elements in set B are also ordered, say B1, B2, B3 and BM. Now this again is rearrangement of elements in set. So nothing has changed in the question. Now we need to define functions from A to B such that FAI is less than equal to FAJ whenever I is less than J. Now there is an equality sign here. So it is no longer an increasing function here. Now how do we solve this question? Now one way of solving this problem can be, we can say that suppose the number of elements in A which are mapped to B1 is, say, N1. Number of elements in A which are mapped to B2, they are N2. And number of elements which are mapped to BM is NM. Now each of the element in A, it must be mapped to 1B. So from here we can say N1 plus N2 plus N3 plus Nm, and this value, it must be equal to N. Now we need to find number of non-negative integral solution of this equation. Number of non-negative integral solution of this equation will be N plus M minus 1 Cn. So number of non-decreasing functions from A to B will be given by N plus M minus 1 Cn. Now how does this work? Suppose one case is when all the elements, they are mapped to B1. So that case will correspond to the solution when the value of N1 is 10 and all the remaining variables, they take the value 0. Another case could be when suppose two of them, they are mapped to B1 and then remaining N minus 2, they are mapped to B2. So it could be 2 N minus 2 and then rest all 0. So all the possible non-decreasing mapping from A to B will correspond to solution of this equation, which is N1 plus N2 plus N3 plus Nm equals M, and this solution is given by N plus M minus 1 Cn. And the same formula works for number of non-increasing functions. Now another method to work out the same formula is, suppose we consider two sets A and B, which are 1, 2, 3 all the way up to N. And then this set B containing elements 1, 2, 3 up to M. Now there is a one-to-one correspondence between number of non-decreasing functions in this case to number of non-decreasing functions in any general case. Now here we need to define functions from A to B such that fx is less than equal to fy whenever x is less than y. Now we'll define another set which is, say, B1, and this B1 is 1, 2, 3 up to M, and then we'll have M plus 1, M plus 2 and M plus N minus 1. Now what we'll do is we'll define a function, say G, from A to B1 such that Gn is Fn plus N minus 1. So in other words, we can write G1 as F1, G2 as F2 plus 1, G3 as F3 plus 2, and Gn as Fn plus N minus 1. Now this function f, it is non-decreasing if and only if when this function g is strictly increasing. Now basically this transformation of f to g is a bijection from non-decreasing functions from a to b to strictly increasing functions from a to b. Now for this set g, we can find number of strictly increasing functions. Now for g, there are m plus n minus 1 elements, and for these n elements, we need to choose n elements from these, and they have to be ordered in ascending order, which can be done in m plus n minus 1 c n ways. So number of strictly increasing functions g from a to b1 is m plus n minus 1 cn, and which is equal to number of non-decreasing functions f from a to b. So number of non-decreasing functions is again m plus n minus 1 cn. So this is how we find number of non-increasing or non-decreasing function for given two sets a and b.
Now question number 16 is, let A be the set containing 10 elements a1, a2, a10, and B is the set having only two elements 1 and 2. Now it says we need to find number of functions defined from a to b such that sum of fa1 up to fa10, it is an even number. Now this sum, it will be an even number when we have even number of elements mapped to 1 and remaining even number of elements mapped to 2. Now what are the possibilities? Now what we'll do is we'll make a table of all such possibilities. So here we let number of FAI which are mapped to 1, and here we let number of FAI which are mapped to 2. Now one such way is when this value is 10, this is 0. Another one is 8, 2, 6, 4, 4, 6, 2, 8 and 0, 10. In all these 6 cases, this summation FAI, it will be an even number. Now how many such functions exist in which all the 10 elements, they are mapped to 1 and none of the element is mapped to 2? This can be done in simply 10C, 10 ways. Now what about this? 8 of these numbers are mapped to 1. Which 8 elements? So here we need to select 8 elements from these 10 elements. So it can be done in 10C 8 ways. Now the next one in the same way will be 10C6, and the same way it will go all the way up to 10C0. So total number of such functions will be 10C0 plus 10C2 up to 10C10. Now we know that NC0 plus NC2 plus NCn, it is nothing but 2 to the power of n minus 1. So this value will be 2 to the power of 10 minus 1, which is 2 to the power 9, and that is 512, and that's your option B.
Now in question number 14, we are given two sets A and B, and we need to find number of functions from A to B such that for every x belongs to A, there is 1 and exactly 1 y with y unequal to x and fx equals f. That means for each and every element, there must exist another element such that the value at x must be same as value at y. So that means for these 6 elements, we need to form 3 pairs. And 2 elements in the given same pair, they must be mapped to same element. So that's how we can fulfill this condition that for every x, there is 1 and exactly 1 value of y. So first thing, what I need to do is I need to distribute these 6 points in the pair of 2, 2 and 2. So in how many ways can it be done? So it can be done in factorial 6 upon factorial 2 whole cube upon factorial 3. So now what we have done is we have distributed these 6 points in a group of 2, 2 and 2. Now we need to find image of these 3 groups. So for the image of these 3 groups, we need to choose 3 elements from this given set B. Now out of these 5 elements, we can choose 3 elements in simply 5C 3 ways. Now we have 3 groups and we have 3 elements. Now we need to map these groups with these given images. So now these 3 groups in A can be mapped to these 3 elements in B in simply factorial 3 ways. So the total number of such functions will be factorial 6 upon factorial 2 cube, factorial 3, 5C3 into factorial 3. Now factorial 3 will cancel
Now this is factorial 6. Factorial 2 cube is 8 and 5c3 is 10. So this is 720 into 10 divided by 8, which is simply 900. So number of such functions is simply 900, which is option number C.
Now here the question is, if x1 plus x2 plus x3 up to xr is n, then number of non-negative integral solutions is given by n plus r minus 1 cn, and number of positive solutions is given by n minus 1 c r minus 1. Now the first question is, if a, b, c, b, three natural numbers in AP, then number of solutions of a plus b plus c equals 21 is. Now since a, b, c are in AP, that means 2b equals a plus c. Value of b will be simply 7. So this b, it is fixed. So here we'll have this condition that value of a plus c, it must be 14, where a and c are natural numbers. So the possibilities are, if a is 1, c is 13, 2 and 12, and you go all the way up to 13 and 1. So there are 13 such cases. So there are 13 ways in which we can select these three natural numbers in AP, so that a plus b plus c is 21. So the correct option is this option C. Now the next one is, number of ways of distributing 22 identical toys among 4 children when each child must get an odd number of toys is equal to which of the following. Now suppose first child gets 2n1 plus 1 toys, second child gets 2n2 plus 1 toys, third child 2n3 plus 1, and fourth child 2n4 plus 1, where any ni is non-negative integer. Now sum of all the toys will be 2n1 plus n2 plus n3 plus n4 plus 4, and it is equal to 22. So 2n1 plus n2 plus n3 plus n4 will be 18. We'll get this equation as n1 plus n2 plus n3 plus n4 equals 9, and we need to find number of non-negative integral solutions. Number of non-negative integral solution is given by n plus r minus 1 c r minus 1, so which is 12c3. So the correct option is 12c3, which is same as 12c9. That's your option B. Now here the question is, we need to find number of positive integral solutions of x plus y plus z equals 10, where x, y and z are unequal, and it is 20 plus k. We need to find value of k. Now first we will find total number of positive integral solutions of this equation, and it is given by n minus 1c r minus 1, which is nothing but 9c2, and 9c2 is nothing but 36. Now from these total cases, we have to remove all these cases. The variables may be equal. So taking this first case, if x equals y equals z, we'll get 3x equals 10, and we won't get any integral solution in it. Now we'll take the second case where x is equal to y, but it is unequal to z. Now we can write this as 2x plus z, and it'll be equal to 10. Now here this variable x, it can take the value from 1 to 4. So value of x can be 1, 2, 3 and 4. Now if we take x as 1, we'll get z as 8, then 6, then 4, and z equals 2. So we'll have 4 such cases. Now we'll have 2 more cases when y equals z and when x equals z. So it will be simply 3 into 4, which is 12 cases. So from these 36 cases, we have to remove these 12 cases. Then we'll get number of positive integral solutions where x, y and z are unequal. So total number of positive integral solutions will be simply 36 minus 12, and which is 24, and it is nothing but 20 plus 4. Value of k here is simply 4, and that is the answer to this question. Now the question is, how many different ways can 15 candy bars be distributed between Ram, Sham, Ghanshyam and Balram if Ram cannot have more than 5 candy bars and Sham must have at least 2, and assume all candy bars are alike? Now, if all candy bars are alike, we can use equation method. So suppose the distribution is R plus S plus G plus B, and it must be equal to 15, where R is less than or equal to 5, and where S is greater than or equal to 2. Now, first we'll simplify this case where S is greater than or equal to 2. So what we'll do is we'll write this S as 2 plus S dash. Now, where S dash is greater than or equal to 0, we can write this equation as R plus S dash plus G plus B will be equal to 13, where R is less than or equal to 5, and where S dash, G and B, they are 0 or greater than 0. Now, in order to find this condition, what we'll do is we'll find the solution to this equation. R S dash G plus B equals 13 when R S dash G and B, it is greater than or equal to 0, and from this we'll subtract all the cases where R plus S dash plus G plus B is 13, but where R is greater than or equal to 6, because maximum value of R in this case is 5. So R is greater than 6 and S dash, G and B, it is greater than or equal to 0. Now here the solution is N plus R minus 1, C R minus 1, and then minus. Now here we can write this R as 6 plus R dash. Now if we write this R as 6 plus R dash, we'll get this equation as R dash plus S dash, G plus B, and will be equal to 7. So here will be N plus R minus 1, C R minus 1 will be 16C3 minus 10C3. Now 16C3 is 16 into 15 into 14 divided by 6 minus 10 into 9 into 8 divided by 6. Now this is 5, 2, 7, and here will be 3 and 4. 560 minus 120, which is 440. So total number of ways of distributing these candies will be simply 440. Now the question is, find the number of distinct throws which can be thrown with n 6-face normal dice which are indistinguishable among themselves. Now, what we'll say is, of these n throws, we get n1 number of ones, n2 number of twos, n3 number of threes, and n6 number of 6. Now, n1 plus n2 up to n6, it must be equal to n, and we have to find number of non-negative integral solutions of this equation. Non-negative integral solution. Now, number of non-negative integral solutions is given by n plus r minus 1, c r minus 1, which is simply n plus 5, c5, and that is the answer to this question.
Find the number of positive integral solutions to this inequality. 3x plus y plus z is less than or equal to 30. So we know that each of this x, y and z, they should be 1 or greater than 1. Now since it is an inequality, I'll introduce a dummy variable. So I'll write 3x plus y plus z plus t equals 30, where each of this x, y and z, it should be 1 or greater than 1, and t should be 0 or greater than 0. Now what I'll do is, I'll also change this x, y and z so that I can have symmetry in the problem. So I'll replace x with 1 plus x dash, y with 1 plus y dash, and z with 1 plus z dash. I'll get this as 3 plus 3x dash, 1 plus y dash, 1 plus z dash plus t equals 30. So I'll write this equation as 3x dash plus y dash plus z dash plus t, and this is equal to, so this is 5. So it will be 25, where each of x dash, y dash, z dash and t, they should be 0 or greater than 0. Now we need to solve this equation. Now we can write this equation as y dash plus z dash plus t is equal to 25 minus 3x dash. Now what are the possible values of x dash? So minimum value of x dash is 0. And what is the maximum value? Maximum value is 8. So the value of x dash should lie between 0 and 8. Now we have to find number of non-negative integral solutions to this equation. So number of non-negative integral solution, it is given by 25 minus 3x dash n plus r. R in this case is 3 minus 1. See r minus 1. So which is 27 minus 3x dash C2. I can also write it as 27 minus 3x dash 26 minus 3x dash divided by 2. So we'll multiply them, we'll get 1 by 2, 702 minus 159x dash and plus 9x dash square. Now, if we have to find total solution, then we have to take the summation of x dash from 0 to 8. So, number of positive integral solution is given by this summation where this x dash varies from 0 to 8 and it is 1 by 2, 702 minus 159x dash plus 9 x dash square. So then it will be, so this is 1 by 2 and then 702 and this summation. So this summation is 9 minus 159 and this is n plus 1 by 2. So it is 8 into 9 by 2 and then plus 9 and this is n plus 1, 2n plus 1 whole divided by 6. So we'll get 1 by 2, 6318 minus 5724 plus 1836 and this value is 1215. So number of positive integral solution of this inequality is 1215.
Now question number 24 is, what is the number of ordered pairs ABC where ABC are positive integers not necessarily distinct such that A into B into C is 1000. So we can write ABC as 2 cube into 5 cube. Now this A, let it be of the form 2 to the power x1, 5 to the power y1, let B be 2 to the power x2, 5 to the power y2 and C be 2 to the power x3 into 5 to the power y3. Now we'll multiply them, then A into B into C will be 2 to the power x1 plus x2 plus x3 into 5 to the power y1 plus y2 plus y3 and it will be equal to 2 cube into 5 cube. Now we'll compare, we'll get these two conditions. We'll get these two conditions, x1 plus x2 plus x3 equals 3 and y1 plus y2 plus y3 equals 3. Now we have to find number of non-negative integral solutions. So number of non-negative integral solutions is given by 3 plus 3 minus 1, C3 minus 1 which is 5C2 and for this also it will be 5C2. So number of such triplets will be 5C2 into 5C2 and which is 10 into 10 and that is 100 and that's your option B.
Now here the question is, the number of combinations of n together of 3n letters of which n are A, n are B and the rest unlike is n plus 2 to the power of n minus 1. Now we have n A's, n B's and the rest n are different. We can write all the possibilities of choosing A as 1 plus x square up to x to the power n and it'll be same for B also. So it'll be 1 plus x square up to x to the power n into, now for each of these n distinct objects, we have two possibilities. Either it won't be selected or it'll be selected. So it'll be 1 plus x to the power n and from this we have to select n things. So we need to find coefficient of x to the power n. Now we can write this as 1 minus x to the power of n plus 1 upon 1 minus x whole square into 1 plus x to the power n and we can also write this as 1 minus x to the power n plus 1 whole square into 1 plus x to the power n into 1 minus x to the power minus 2. Now in this series, it will be 1 and then powers of x will be greater than n. So from here we will only get 1. That means from this product we have to find coefficient of x to the power n. So it will be coefficient of x to the power n in 1 plus x to the power n into 1 minus x to the power minus 2. Now we'll get coefficient of x to the power n if we select x to the power r from this series and x to the power n minus r from this series. Now this coefficient will be given by this summation r varies from 0 to n. Now coefficient of x to the power n minus r will be nc n minus r into coefficient of x to the power r. Now in this case value of n is 2, so it will be 2 plus r minus 1 cr. So we can write this as this summation r varies from 0 to n. Now nc n minus r is same as ncr into, and this is r plus 1 cr. Now r plus 1 cr is r plus 1 c1. So we can write this as this summation r varies from 0 to n r plus 1 into ncr. Now using binomial expansion, we have to find the value of r plus 1 ncr. Now one way of doing it can be, we can write binomial expansion of 1 plus x to the power n, and it is summation r varies from 0 to n ncr into x to the power r, but here we need r plus 1. So what we'll do is, we'll multiply x, we can write x into 1 plus x to the power n, and it will be equal to this summation r varies from 0 to n ncr into x to the power of r plus 1, and then we'll differentiate both sides. Now if we differentiate both sides, we can write this is x n into 1 plus x to the power n minus 1 plus 1 plus x to the power n, and here will be the summation r varies from 0 to n r plus 1 ncr into x to the power r. Now we'll put x as 1. Now we put x as 1, this right hand side it will be this summation r varies from 0 to n r plus 1 ncr, and here on the left hand side it will be n into 2 to the power of n minus 1 plus 2 to the power of n. Now we'll take 2 to the power of n minus 1 common, so it will be n plus 2 into 2 to the power of n minus 1. So coefficient of x to the power n will be n plus 2 into 2 to the power of n minus 1, which is what we need to do.
Now I got this interesting question from one of my students, and the question is, if an examination has 20 questions, for each question the marks that can be obtained are either -1, 0 or 4, and if S is the set of possible total marks that a student can score in an examination, then we need to find total number of elements in set S. So that is, if in a question a student can get either -1 or 0 or +4, and there are 20 such questions, what are the possibilities of total marks that this student can score? So one way of solving this question is, for each question we know there are 3 possibilities. Either a student will score -1 or 0 or 4, and we can express it by this simple polynomial, which is either a student will score 0, so which is represented by this term x to the power 0, or -1 or 4. So that is, for each question there are 3 possibilities, and which are 1 upon x plus x to the power 4. So total number of ways of scoring on this question will be 1 plus 1 upon x plus x to the power 4 to the power 20. Now in order to find all possible total marks that a student can score, we need to find number of distinct terms in this expansion. Number of distinct terms in the given expansion. Now, how do we find number of distinct terms in this expansion? So I cannot use that formula n plus r minus 1 cr minus 1, because it is applicable only when the variables are unrelated or distinct. So what I'll do is, I'll write this expansion 1 plus 1 upon x plus x to the power 4 to
to the power 20 as x to the power 4 plus 1 plus 1 upon x to the power 20. And if I'll use binomial expansion, I can write r varies from 0 to 20, 20 CR x to the power 4, 20 minus r, and 1 plus 1 upon x to the power r. Now if I'll expand this series, I can write the series as 20C0 x to the power 80, 1 plus 1 upon x to the power 0, 20C1 x to the power 76, 1 plus 1 upon x, 20C2 x to the power 72, 1 plus 1 upon x whole square, 20C3 x to the power 68, 1 plus 1 upon x to the power 3, and then plus this summation where r varies from 4 to 20 x to the power 20 minus r into 1 plus 1 upon x to the power r. Now here I'm not interested in the expansion of this series. So what I'm interested in is number of distinct terms. So what I'll do is I'll just count what are the powers of x that will be present in this expansion. So this expansion will have x to the power 80. Then here we'll have x to the power 76. And if I'll multiply it with 1 upon x, I'll get x to the power 75. Then from this one, now 1 plus 1 upon x, it will have 1 upon x and 1 upon x square. So here I'll get x to the power 72, x to the power 71, x to the power 70. Now with 68, I'll have 1 upon x, 1 upon x square and 1 upon x cube. So here I'll get x to the power 68, x to the power 67, x to the power 66, x to the power 65. And hereafter we know that this r is greater than 4. So it will contain these 4 consecutive terms. So 1 upon x to the power 0, x to the power 1, x to the power 2, x to the power 3. So from here we'll get all the consecutive powers of x. So starting from 68, we'll get all the consecutive powers of x up to this 1 plus 1 upon x to the power 20. And there I'll get x to the power minus 17, x to the power minus 18, x to the power minus 19, and x to the power minus 20. So in this expansion, I'll have these terms starting from x to the power minus 20 to x to the power 68, and then we'll have these 6 more terms. So now I'll need to count number of distinct terms in this expansion. So I know that from 80 to 20, it'll be total 80, and then plus we also have x to the power 0, and then plus 20. So that's 101. And then minus, what are the missing terms? Missing terms here are 77, 78, 79, 73, 74, and then x to the power 69. So that is, there are 6 terms which are missing. So 101 minus 6, so that is 95. So the total number of elements in set S is 95. So there are 95 different possibilities in which the student can score in an examination. Now we'll come to non-consecutive selections. So suppose we have n objects which are arranged in a row. We have to select objects from these arranged objects so that no 2 objects they are consecutive. So here we have n objects which are arranged in a row. Say A1, A2, A3, A4, A5, and it goes all the way up to AN. Now from these n objects, we have to select r objects so that no 2 objects are consecutive. So problem is, from n objects, we have to select r objects so that no 2 objects are consecutive. So we call this as non-consecutive selection. So what we'll do is, suppose we have selected R objects, say A2, A4. So in this way, suppose we have selected these R objects so that no two objects are consecutive. Now what we'll say is, number of objects before first selection is say x1. Number of objects between these two selections is say x2. Then again for the third one, suppose it is x3. And finally, after the last object, which is rth object, it will be x r plus 1. See, it is clear that suppose we have 5 objects. If we select 2 objects, there will be 3 partitions. So if we have r objects, there will be r plus 1 partitions. So number of elements in between any two selection or on the edges will be x1, x2, x3 and xr plus 1. Now total number of elements which we have selected is r, and the total number of elements which we have not selected is n minus r. So basically this value, which is x1 plus x2 plus x3 plus xr plus 1, it must be equal to these remaining elements, and which is n minus r. Now the question says we have to select them in such a way that objects are non-consecutive. If objects are non-consecutive, that means in between any two selection, there will be at least one object. So from here we can write this condition that x2, it should be 1 or greater than 1. x3 should be 1 or greater than 1. x4 again should be 1 or greater than 1. In the same way, xr should be 1 or greater than 1. What about x1 and xr plus 1? Now the case can be, we have selected this first element and then we have taken a gap, and then we can select say third or fourth or any other element. So this x1 and xr plus 1, they can take a value 0. So here x1 and xr plus 1, they should be 0 or greater than 0. So we'll need to find total number of solutions of this linear equation x1 plus x2 plus x3 plus xr plus 1 equals n minus r, such that x1 and xr plus 1 should be 0 or greater than 0, and all other variables should be 1 or greater than 1. So what we'll do is, in order to achieve some symmetry in this problem, we'll change all these variables x2, x3 and xr. So we'll write x2 as 1 plus x2 dash. Now since x2 is greater than or equal to 1, x2 dash will be greater than or equal to 0. In the same way, we can write this x3 as 1 plus x3 dash. Again, x3 dash will be greater than or equal to 0. And finally, xr, we'll write it as 1 plus xr dash, and will be xr dash should be greater than or equal to 0. So we'll substitute x2, x3, xr in terms of x2 dash, x3 dash and xr dash. So we can write the same equation as x1 plus 1 plus x2 dash, 1 plus x3 dash, and then 1 plus xr dash and plus xr plus 1, and it'll be equal to n minus r. Now here, each of these variables, which are x1, x2 dash, x3 dash, xr dash and xr plus 1, they are 0 or greater than 0. So basically we need to find number of non-negative integral solutions of this equation. So we can write this equation as x1 plus x2 dash plus x3 dash plus xr dash plus xr plus 1, and then there'll be this 1, 1, 1 starting from 2 to r, so it'll be r minus 1 times. So it'll be simply r minus 1, and that is n minus r. So we can write this as x1 plus x2 dash plus xr dash plus xr plus 1, and it will be n minus 2r plus 1. So we need to find number of non-negative integral solutions of this equation. So non-negative integral solution of this equation. So we know that number of non-negative integral solution of any equation is given by n plus r minus 1 c r minus 1. N, which in this case is n minus 2r plus 1 plus r, and r in this case is r plus 1 minus 1, and c r minus 1, which in this case is r plus 1 minus 1. Now here 1 and 1, it will cancel. So we'll write this as n minus r plus 1 cr. So the total number of ways in which we can select r objects from n arranged objects so that no two objects are consecutive is given by this formula, which is n minus r plus 1 cr. So if the problem is we have n objects which are arranged in a row and we have to select r objects so that no two objects are consecutive, then this selection can be made in n minus r plus 1 cr ways. Say for example, the question is, if the n things are arranged in a row, then show that number of ways of selecting 4 of the things so that no two of which are consecutive is. So from these n objects arranged in a row, we have to select 4 objects so that no two of them are consecutive. So we know that number of ways of selecting r objects from n objects so that no two objects are consecutive is n minus r plus 1 cr. Now in this case, n is simply n, but r is 4. So the total number of ways in which we can select these 4 objects are n minus 4 plus 1 c4, and there'll be n minus 3 c4. So we'll write this as n minus 3, n minus 4, n minus 5, n minus 6, and then it'll be 4, 3, 2, 1. So that should be n minus 3, n minus 4, n minus 5, n minus 6 upon factorial 4. So the total number of ways of selecting 4 objects from n things which are arranged in a row so that no two of which are consecutive is n minus 3, n minus 4, n minus 5, n minus 6 divided by factorial 4. Now we'll discuss non-consecutive selection on a circle. So suppose we have n objects which are arranged on a circle. So suppose this is A1, A2, A3, A4, some AK, and then AN. Now from these n objects arranged on a circle, we have to select r objects so that no two objects are consecutive. So the problem is, from n objects arranged on a circle, select r objects such that no two objects are consecutive. Now problem of selecting objects on a circle is little different from problem of selecting objects in a row. Now we know that on a circle there is no starting point. So on a circle we have to have a starting point from where we can start defining the problem. I have made a video on cyclic permutation where I have shown that why on a circle number of arrangements is factorial n minus 1 and not factorial n. So I'll put the link to that video in the description below. So in order to start, we'll first need to select any one element. So this one object from these n objects can be selected in NC1 ways. Now, once we have selected this object, suppose A2, then we can select all the remaining R objects. Now, number of objects in between any two selection is say XR. Say it is X1 and then X2 and then X3. Now on a circle, there'll be R such variables. So we need to find these remaining numbers which are X1 plus X2 plus X3 and plus XR. And what are the total number of remaining elements? Total number of remaining elements is simply N minus R. So we need to find number of solution of this equation when each of this X1, X2 and XR is 1 or greater than 1. Now in this case, we'll just need to find number of positive integral solutions. So number of positive integral solutions will be, this is NC1, and here number of positive integral solution of any equation is given by n minus 1 c r minus 1. So here n is n minus r, so it will be n minus r minus 1 and then c r minus 1. So it will be c r minus 1. So now we have selected this first element and then according to this selection, we have already taken this condition that in between two selections, there has to be at least one element. Now still the problem is not complete, and I'll tell you why it is not complete. Now suppose we have started with A2 and then we have selected A4, AK and AN. Now we get the same selection if we start with A4 and then we continue with AK, AN and A2. So again that selection will be same as this previous selection. We can end up getting the same selection with AK and we can end up getting the same selection with AN as well. So total number of distinct selections will be this entire value whole divided by number of variables, which in this case is simply R. So this value will be R. So the total number of ways in which we can select R objects from N objects on a circle so that no two objects are consecutive, it will be N into N minus R minus 1, C R minus 1 upon R. So selecting R non-consecutive on a row is distinctly different than selecting R non-consecutive on a circle. Now we take this question, which is if n things are arranged in a circle, then show that number of ways of selecting 4 of these things so that no two of which are consecutive is n, n minus 5, n minus 6, n minus 7 upon factorial 4. So we know that formula of selecting R object so that no two are consecutive is n into n minus R minus 1 C R minus 1 upon R. So in this case, n is simply n and R is 4. So it will be n minus 4 minus 1 C 4 minus 1 upon 4. So we can write this as n into n minus 5 C3 upon 4. So it will be n and then n minus 5, n minus 6, n minus 7 upon, we already have this 4 and then it will be 3, 2, 1. 4, 3, 2, 1 is factorial 4 and in the numerator we have n, n minus 5, n minus 6 and n minus 7. So this is how we select 4 objects so that no two of which are consecutive when n things are arranged on a circle. Now previously in consecutive selections we have done one problem in which we did figure out number of triangles that can be formed from the vertices of this octagon so that they do not have a side common with that of octagon. Now another way of solving the same problem can be if we select any 3 vertices on this octagon which are non-consecutive, then this triangle and octagon will not have any common side. So if we have to find number of triangles formed from the vertices of regular octagon such that they do not have a common side with octagon, it will be given by number of selecting 3 vertices from these 8 vertices so that no 2 vertices are consecutive. So formula for this is n into n minus R minus 1 C R minus 1 upon R. Now here in this case, n is 8 and R is simply 3. So it will be 8 into 8 minus 3 minus 1 C 3 minus 1 upon 3. So it will be 8 and then 8 minus 4 is 4. So it will be 4 C2 upon 3. So it is 8 into 6 upon 3 and which again is 16. So the total number of triangles that can be formed from the vertices of octagon so that they do not have a side common with that of octagon is simply 16 by using this formula. Today we'll discuss very important thing in permutations and combinations, and which is distribution of balls into boxes. Now we have generally 4 cases: identical balls, identical boxes, distinct balls, identical boxes, identical balls, distinct boxes, and distinct balls and distinct boxes. So we'll be discussing all these 4 cases, and we'll be discussing all these cases in context of this given problem, and then we'll also discuss the general formula for such problems. So the condition here is we need to distribute 5 balls in 3 boxes so that no box is empty. So we'll start with the first case, and that is if we have identical balls and identical boxes.
So now we have 5 balls which are identical. And we have 3 boxes which are also identical. Now in how many ways we can distribute these 5 balls in 3 boxes so that no box is empty? So we know that if we have to distribute these balls, then it can be done in either 2, 2 or 1 way, or it can be 3, 1 or 1 way. So there are only 2 ways with which we can distribute these 5 balls in 3 boxes so that no box is empty. So these are the only 2 ways. Either it is 2, 2, 1 or it is 3, 1, 1. And since balls and boxes, they are both identical, then it doesn't matter which ball goes to which box. So the problem basically is we'll need to partition 5 in size of 3. So in how many ways can it be done? It can be done in only 2 ways. Either it will be 2 plus 2 plus 1, or it will be simply 3 plus 1 plus 1. Now, how do we solve any general problem? Suppose we have n identical balls and r identical boxes. Then this number is same as partition of number n in R. So we have to find total number of ways in which we can partition a number n in R compartments. Now when n is large, it is very difficult to find this P and R. Suppose we say we need to find number of ways of distributing 9 identical balls in 3 identical boxes. So in that case, this n is 9. Now how do we solve such cases? So for that we have one theorem, and that theorem, it might come to our rescue, and the theorem is we can write this P n R as this summation P n minus R comma K, where K varies from 1 to R. So say for example, suppose we have a question where we have 9 identical balls and 3 identical boxes. We'll need to find number of ways in which we can distribute 9 identical balls in 3 identical boxes so that no box is empty. So we know that it is given by this partition P93. We can write this as summation P, now n minus R. N minus R in this case is 6 and 6 comma K, where K varies from 1 to 3. So it'll be P61 plus P62 and P63. So this problem now reduces to partition of 6 in 1. So in how many ways we can partition 6 in one part? So we know that we can do it only in one way. So it'll be simply 6. What about 6 in 2? 6 in 2 is either 5 plus 1 or 4 plus 2 or 3 plus 3. So there'll be 3 ways. And what about 6 in 3? 6 in 3 will be either 4 plus 1 plus 1 or 3 plus 2 plus 1 or 2 plus 2 plus 1, which again is 3. So it'll be 1 plus 3 plus 3. So P61, it is 1, P62 is 3 and P63 is 3. So this result, it comes out to be 7. So the number of ways of distributing 9 identical balls in 6 identical boxes is 7. So any such problem we have to solve using partitions, and there this theorem will come handy if the value of n is large, and this is how we solve such problems. Now if the problem is not asked in an examination and we need to find partition of n into R, then we can also use this partition chart. So here we are given n and R, then using this table we can clearly find out the value of P and R. Suppose we need to find value of P61. So P61, it will be 1. So we have this value 1, and then P62 is 3. We have got the value 3, and then P63 is again 3. So it will be again 3. So it will be 1 plus 3 plus 3, and that again is 7. So this is how we solve problems when the balls are identical and the boxes are also identical. Now we'll come to the second case when balls are identical and boxes are distinct. So here we have 5 balls which are identical, but in this case boxes are distinct. So we have 5 identical balls and 3 distinct boxes. Now in how many ways we can distribute these identical balls in these boxes? So in the first question we have discussed how to distribute these identical balls in identical boxes. So it can be done in 2 ways. Either we can distribute them as 2, 2, 1, or we can distribute them as 3, 1, 1. Now once we have distributed these balls as 2, 2 and 1, now since these 3 boxes they are distinct, so it matters which box has this one ball. It could be either 2 in blue, 2 in green and 1 in black, or it could be 1 in green, or it could be 1 in blue. So we can distribute 2, 2 and 1 in 3 distinct boxes as factorial 3 divided by factorial 2 ways, because here these two numbers they are same. So it can be done in only 3 ways, and we know that it'll be either 2, 2, 1 or 2, 1, 2 or 1, 2, 2. In the same way, we can distribute 3, 1, 1 in 3 distinct boxes as factorial 3, and then again we have 2 1 same, so it will be divided by factorial 2, and this again is 3. So it will be 3 plus 3, and that is 6 ways. So we can write this as 3 1 1, 1 3 1 or 1 1 3. Now the best way to solve such questions is using linear equations. So what we'll say is, we'll say let number of balls in first box be x1, let the number of balls in second box be x2, and number of balls in third box be x3. Then we can simply write this equation as x1 plus x2 plus x3, and it is equal to n, so which is equal to number of balls in this case. So once we have identical objects and we have to distribute these identical objects into distinct groups, then we can always use this linear equation. So here we need to find number of positive integral solutions. So we know that number of positive integral solution is given by n minus 1, which is 5 minus 1c, r minus 1. R in this case is 3, so it will be 3 minus 1. So that should be 4c2, and 4c2 is nothing but 6. So total number of ways in which we can distribute identical balls into distinct boxes is 6. Now if we have general questions, say we have n identical balls and r distinct boxes, then we can simply write this equation as x1 plus x2 plus xr, 1 for each box, and it should be equal to n, and number of positive integral solution is given by n minus 1c r minus 1. So this is how we can find the cases when the balls are identical and boxes are distinct, and each box should have at least one ball. Now we'll come to this third case when balls are distinct but boxes are identical. So here in this case, we have distinct balls but identical boxes. So we have 5 distinct balls. So 1, 2, 3, 4, and 5. So we have 5 distinct balls and 3 identical boxes. So now we need to distribute distinct objects in identical cases. Now in this question, we already know that we can distribute 5 balls in 3 boxes so that no box is empty in either 2, 2 or 1 way, or we can distribute them as 3, 1 or 1 way. Now this question is actually nothing but it is distribution of objects into identical groups. Now how do we distribute 5 objects in a group of 2, 2 and 1? So we know that this can be done in factorial 5 divided by factorial 2, factorial 2, factorial 1, and since we have these two numbers same, we need to divide it with factorial 2. So it will be 120 divided by 8. So it will be 15. Now in the same way, we need to distribute 5 objects in a group of 3, 1, 1. So it will be factorial 5, factorial 3, factorial 1, factorial 1. And since these two, they are identical, we again need to divide it with factorial 2. So it will be again 120. And here it is 6 into 2. So which is 10. So it will be simply 15 plus 10, and that should be 25. So number of ways of distributing 5 distinct balls in 3 identical boxes is 25. So this problem is actually distribution problem, which we generally study in combinations, distribution into non-distinct groups. Now let us discuss more general problem in this. Suppose we have n distinct balls and r identical boxes. So in how many ways we can distribute n distinct balls in r identical boxes so that no box is empty. Now it can be done in S and R ways. So there is a direct formula for this, S and R, and S and R is nothing but it is Stirling number of the second kind. Now how do we find S and R? So there is a formula for S and R. S and R is given by 1 upon factorial R, and then L be RC0 R to the power n minus RC1 R minus 1 to the power n plus RC2 R minus 2 to the power n, and will continue till the end where it will be minus 1 to the power R minus 1 to the power n. So using this formula we can find out this Stirling number S and R, and this S and R is equal to number of ways in which we can distribute n distinct balls in R identical boxes. So we'll use this formula for our question. Now in this, value of n is 5 and value of R is 3. So we need to find S 53. Now S 53 will be 1 upon factorial 3, 3C0, 3 to the power 5 minus 3C1, 2 to the power 5 plus 3C2, 1 to the power 5. So we need to find this number, and this number is S53. Now this is 1 upon factorial 3, which is 6. Now 3 to the power 5. 3 to the power 5 is 243 minus 2 to the power 5, it is 32. 32 into 3 is 96, and then plus 3C2, it is simply 3. So we'll get 246 minus 96. So it will be 150, and 150 divided by 6 is simply 25. So which is the answer to our question. So a general way of solving this question is by finding this Stirling number S and R using this given formula. Now we'll come to our fourth case, which is when the balls are distinct and boxes are distinct. So now we have 5 balls. Which are distinct, and we also have 3 boxes which are distinct. Now with distinct balls and distinct boxes, we need to distribute the balls so that no box is empty. So in the previous case, we have studied that when the balls and boxes are identical, we can distribute them as 3, 1, 1, and then 2, 2, and 1. So what we'll do is, we'll first distribute these 5 balls in a group of 3, 1, and 1, and then we'll arrange this 3, 1, 1 in these 3 boxes. So first we'll go for distribution. Distribution part will be factorial 5 divided by factorial 3, factorial 1, factorial 1, and then these ones are same, so it'll be divided by factorial 2, and then now we have 3 objects, and these 3 objects are to be arranged in these 3 boxes. It can be done in factorial 3 ways. So now it will be 10 into 6, that is 60. And the same way, first we are going to distribute 2, 2 and 1. So it will be factorial 5, factorial 2, factorial 2, factorial 1, and then again these 2 and 2, they are same. So it will be factorial 2, and again we have 3 objects and they are to be arranged in 3 places. It can be done in factorial 3 ways. So here it will be 15 into 6. That should be 90. So total number of ways of distributing 5 distinct balls in 3 distinct boxes is 150. Now what is the general way of solving this problem? General way of solving this problem, when we have n distinct balls and they are to be distributed in r distinct boxes such that no box is empty. Now this problem is given by number of onto functions from a set containing n elements to set containing r elements. We have already done a video on number of onto functions. So I'll provide the link to that video in the description below for your kind perusal. So you can have a look at that video to find out how we have worked out a formula. This number of onto functions is given by r to the power n minus and then rc1 r minus 1 to the power n minus rc2 r minus 2 to the power n, and we'll continue up to minus 1 to the power r minus 1 and then 1 to the power n. So this is the formula for number of onto functions from n to r. So in our case, the value of n is 5 and the value of r is 3. So total number of ways of this distribution will be r to the power n, so will be 3 to the power 5 minus 3c1 2 to the power 5 minus 3c2 1 to the power 5. So 3 to the power 5, it is 243 minus 3c1 is 3 and 2 to the power 5 is 32 and minus 3. So there will be 96. 96 minus 3 is 93. So it will be 243 minus 93, which is nothing but 150. So this is how we can find number of ways in which we can distribute n distinct balls in r distinct boxes. Now coming to this fifth case, when the balls as well as boxes are identical, but boxes are kept in a row. So this scenario is same as when the balls are identical and boxes are different. This case we have already discussed, so we'll not discuss it again. So this is how we solve problems of distribution of balls into boxes when they can be identical or distinct.
And one of the previous videos we have discussed the case where balls are distributed into the boxes when no box is empty. Now in this video we'll be discussing how to distribute balls into boxes if boxes are allowed to be empty. In that video we have discussed the specific case as well as the general case. I'll provide the link to that video in the description below for your perusal. And in this video also we'll be discussing this specific case where 5 balls are to be placed in 3 boxes, as well as we'll discuss general case. Now the first question is, in how many ways we can distribute 5 balls in 3 boxes if both balls and boxes are different? So we have this first case, we have distinct balls and distinct boxes. Now previously when the condition was no box is empty, we have solved the question using number of onto functions. Now for this case, the problem is fairly simple. In this case, we just need to find number of functions that can be defined from the set A containing 5 elements to set B containing 3 elements. Now how do we find total number of functions defined from set A to set B? Now for this first ball, we have 3 choices. So it can be put into any of the 3 boxes. So for the first ball, we have 3 choices. For the second ball also, we have 3 choices, and it will be the same for third, fourth and fifth ball. So total number of ways in which we can put 5 balls in 3 distinct boxes will be 3 to the power 5. So if we take a general case where we have n balls, say B1, B2 and Bn, and we have r boxes,
say B1, B2 and BR, then total number of ways in which we can put these balls in boxes when the balls and boxes both are distinct and the box can be empty. For this first ball, we have R choices. For second ball also, we have R choices. For this nth ball also, we have R choices. So total number of ways of putting n distinct balls in R distinct boxes will be simply R into R into R n times, and there'll be R to the power n. Now we'll consider the second case when balls are identical but boxes are different. So we have identical balls and distinct boxes. Now identical balls and distinct boxes is again r-multiset problem. When the balls are identical and boxes are distinct, we can use linear equations. So we have three boxes. Suppose number of balls in first box is x1, number of balls in second box is x2, and number of balls in third box is x3, and total number of balls, it must be 5. Now any box can have any number of balls. So each of these x1, x2 and x3, they must be greater than or equal to 0, and they must be an integer value. So we have to find number of non-negative integral solutions. Non-negative integral solutions. Now previously, for the case when no box is empty, we have taken number of positive integral solutions. Now here we are taking number of non-negative integral solutions because here 0 is permitted. So number of non-negative integral solution in this case will be n, which is 5 plus r is 3, minus 1, c, r minus 1, and there'll be 7c2. Now we'll take this general case when we have n identical balls and r distinct boxes, then we can write this condition as this linear equation, which is x1 plus x2 plus xr, and it must be equal to n, where each of xi is greater than or equal to 0. We need to find number of non-negative integral solutions. So number of non-negative integral solution. Number of non-negative integral solution in this case is given by n plus r minus 1, c, r minus 1. So this is how we distribute identical balls in distinct boxes. Now we'll take up this third case when balls are different but boxes are identical. So here we have 5 distinct balls and 3 identical boxes. Now how can we distribute these distinct balls in identical boxes? Now since it has distinct balls, it is a distribution problem. So we'll consider 3 cases. Case 1, when all the 5 balls, they're distributed in only one box. Second case, when these 5 balls are distributed in 2 boxes, in 2 non-empty boxes, they can be distributed as either 4-1 or 3-2. And this third case, when all these 5 balls, they are distributed in 3 non-empty boxes. So it can be done in either 3-1 one way or 2-2 and 1 way. Now for this first case, from these 5, we need to select 5, and it can be done in only one way. Now for this second case, we have to distribute this 5 in 2 groups containing 4 and 1. So it'll be factorial 5 divided by factorial 4 factorial 1, and it'll be simply 5. Then we have to distribute this 5 in groups of 3 and 2. It'll be factorial 5, factorial 3 factorial 2, and it'll be simply 10. Now what about 3 1 1? It'll be factorial 5, factorial 3, factorial 1 factorial 1 whole square, and then since these 2 numbers, they are same, so we have to divide it by factorial 2. So it'll again be 10, and here it will be factorial 5, factorial 2 square, factorial 1, and again we have these 2 numbers same, so divide by factorial 2, so it'll be 15.
So we'll add them. Total number of ways will be simply 41. So there'll be 41 ways in which we can distribute these 5 distinct balls in 3 identical boxes. So essentially what you have done is we have used the same formula of distributing distinct balls in boxes if no box is empty, considering 3 separate cases when we have only 1 box, when we have 2 boxes, and when we have 3 boxes. So general case of solving this problem will be, suppose we have n distinct balls and we have r identical boxes, then number of ways of distributing n distinct balls in r identical boxes will be given by this Bell number Bn, and which is nothing but sum of Stirling's number of second kind S nk, where k varies from 0 to r. So for this case, we'll need to find this summation. K varies from 0 to 3 S 5k, which is S50 plus S51 plus S52 plus S53. Now S50 it is 0, S51 is 1, S52 is 15, and S53 is 25. So this value, it again comes out to be 41. And finally we have this case when balls as well as boxes are identical. So here we have 5 identical balls and 3 identical boxes. Now these 5 identical balls are to be distributed in 3 identical boxes. Now this again is nothing but a partition problem. So previously we have partitioned 5 in 3 sets. Now since in this case empty boxes are allowed, so we need to find this partition P51 plus P52 plus P53. So if no box is empty, then we just have to find P53. But here we have to find P51 plus P52 plus P53. Now in how many ways we can partition 5 in 1? So there is only one way. Now what about 5 in 2? Now 5 in 2 can be either 1 plus 4 or 3 plus 2. So there will be 2 ways, and 5 in 3 will be 1 plus 1 plus 3 or 2 plus 2 plus 1. So we have 2 ways here. So total number of ways will be simply 5. So we can distribute 5 identical balls in 3 identical boxes in 5 ways. We have to write its general formula. So we have n identical balls and r identical boxes. Then all we need to do is we'll need to find this P nk, where k varies from 1 to r. So we have to find some of these partitions P and k. Now for our problem, this is summation k varies from 1 to 3 P5k, which is P51 plus P52 and P53. Now we can use either this partition table P51 is 1, P52 it is 2, and P53 is 2. So it'll be 1 plus 2 plus 2, which again is 5, or we can use recurrence relation for the partition function, which we have discussed in the previous video. So this is how we distribute balls into boxes if boxes are allowed to be empty.
Now the question is, find the number of combinations and number of permutations of the letters of the word parallel taken 4 at a time. Now if we consider this word, it has 3 L's, 2 A's, 1 P, 1 R and 1 E. That is, in total it has 8 letters. Now first we need to find number of combinations and number of permutations of letters of the word parallel taken 4 at a time. Now there are 2 ways of solving such questions, and the first one is we can look at different cases possible. Now the first case possible is, 3 alike, 1 distinct. Second case is 2 alike, 2 alike. Third case is 2 alike, 2 distinct. And fourth case is all 4 distinct. Now first we'll talk about just selection. Now 3 alike, it can only come from 3 else. So it will be 1C1 and then 1 distinct. It can be any one of the 4. So it will be 4C1. So it is simply 4 cases. Now 2 alike and 2 alike, it can come from 3 else and 2 a's. So it will be simply 2C2, which is only 1 case. Now 2 alike, so it will be 2C1 and 2 distinct will be 4C2. So there will be 2 and 6, there will be 12, and all 4 distinct will be 5C4, which is 5. So total number of combinations it will be 4 plus 1 5, 5 plus 5 10, 10 plus 12 it will be simply 22. Now if we need to find its permutations also, so now here we have 3 alike and 1 distinct. So now we need to arrange them also. Now we can arrange them in factorial 4 divided by factorial 3 ways. So there will be 16 ways. Now here will be 2 alike and 2 alike. So factorial 4 divided by factorial 2 factorial 2, and there will be 6. Now here will be 12 factorial 4 divided by factorial 2. It will be 12 into 12, that is 144, and here it will be 5 into factorial 4, and there will be 5 into 24, and that is 120. So number of permutations will be given by 16 plus 6. 16 plus 6 is 22. 22 plus 120 is 142. 142 plus 144 is 286. So number of permutations is 286. Now another way to solve such question is using this series. Now since we are talking about 4-letter word, it will be factorial 4. Now for these 3 else we have 4 possible arrangements. So it will be 1, x upon 1, x square upon factorial 2, x cube upon factorial 3. Now for 2 a's it will be 1 plus x square upon factorial 2. For each of p, r and e, there will be these 3 cases, which is 1 plus x, 1 plus x and 1 plus x. Now from this we need to find coefficient of x to the power 4. Now we can write this as factorial 4 1 plus x square upon factorial 2 plus x cube upon factorial 3, and here will be 1 plus x square upon factorial 2, and here 1 plus x cube will be 1 plus x cube plus 3x plus 3x square. Now we'll multiply these two. We can write factorial 4 1 plus x square upon factorial 2 plus x cube upon factorial 3, and here will be 1 plus x square upon 2 plus x cube plus x4. We'll discard all the parts which are greater than 4 plus 3x plus 3x square plus 3x cube by 2 plus 3x square plus 3x cube plus 3x to the power 4 divided by 2. We can write this as factorial 4 1 plus x square by 2 x cube by 6, and here will be 1 plus, now this is x plus 3x 4x. Now we have 3x square plus x square by 2, so there will be 13x square by 2 plus x cube 3x cube plus 3 by 2x cube. So there will be 11 by 2x cube and plus 5 by 2 into x to the power 4. Now we need to find coefficient of x to the power 4. So it will be this factorial 4. Now this x to the power 4 into 1, which is 5 by 2. Now this x into x cube, which is 11 by 2. X square into x square will be 13 by 4. And plus x cube into x, which is 4 by 6. And this value will be 286, which is same as what we have worked out in the previous case. So these are the two possible methods. Now here the question is, there are counters available in 7 different colors. The counters are all alike except for the color, and there are at least 10 of each color. Find the number of ways in which an arrangement of 10 counters can be made, and we have found how many of these will have counters of each color. Now we have 10 positions. Then for each position we have 7 different choices. So it will be 7 into 7 into 7 up to 10 times. So total number of ways in which these 10 counters can be arranged is simply 7 to the power 10. Now this part B is how many of these will have counters of each color. That means it should have 7 counters of different color, and then we are left with 3 other counters. Now we'll consider all the possibilities. The first possibility is when all these 3 counters are of same color as any one counter. So there will be these 4 alike and 6 distinct. Now this 3 is 2 plus 1. In that case we'll have 3 alike, 2 alike and 5 distinct. And this third case, when it is 1, 1 and 1, then we'll have 2 alike, 2 alike, 2 alike and 4 distinct counters. Now 4 alike, it can be selected in 7C1 ways, and then it will be 6C6, and it will be factorial 10 divided by factorial 4. Now for the second case, 3 alike, it is 7C1, 2 alike, it is 6C1, 5C5, factorial 10 divided by factorial 3, factorial 2. Now 2 alike, 2 alike and 2 alike will be 7C3 and then 4C4 into factorial 10 divided by factorial 2 cube. Now this is factorial 10 into 7 by 24. This is factorial 10 and this is 42 and this is 6 into 2. So it will be 7 by 2 into factorial 10 and here it will be 35 by 8 into factorial 10. Now if we add them all up, then number of possible arrangements will be factorial 10 7 by 24 plus 7 by 2 plus 35 by 8, which is 49 by 6 into factorial 10. Now here the question is, let Fn denote the number of ways in which n letters go into n envelopes so that no letter is in correct envelope. Where n is greater than 5, then Fn minus n Fn minus 1 equals what? Now this is nothing but this is recursive relation in derangements, which we have already studied. So suppose we have these n letters which are given by L1, L2, L3 and Ln, and then we have n envelopes which are given by E1, E2 and En. Fn is total number of ways in which we can distribute these letters into envelopes so that no letter is in correct envelope. Now for that what we'll do is we'll assume that in this E1 there is one of the letter
from these n minus 1 letters. So any one letter for E1, it can be selected in n minus 1 C1 ways. So this is n minus 1 C1. Now suppose the selected letter is LK. Now we have two cases. Case 1, when this LK goes into E1 and L1 goes into EK, then we are left with derangement of remaining n minus 2 letters. So it will be nothing but F n minus 2. Or this other case where LK goes to E1 but L1 it doesn't go to EK. Now in this case we'll have derangement of remaining n minus 1 letters. So it will be simply F n minus 1. So from here we will get this recursive relation that Fn equals n minus 1 Fn minus 2 plus Fn minus 1. Now we can write this as Fn and this is n minus 1 Fn minus 2 plus Nf n minus 1 minus F n minus 1. Now we will take it on the left hand side. We can write Fn minus n Fn minus 1. It will be n minus 1 Fn minus 2 minus Fn minus 1, and that's your option B. Now this question is actually nothing but proof of recursive relation in derangement, which is Dn. It is given by n minus 1 into Dn minus 2 plus Dn minus 1. Now here the question is, let An denotes number of all n-digit positive integers formed by the digits 0 and 1 or both such that no consecutive digits are 0. Let Bn is number of such n-digit numbers ending with 1 and Cn is number of n-digit numbers ending with 0. So for this An, we have this n-digit number and this last digit, it may be either 1 or 0. Now if the last digit is 1, it is Bn, and if last digit is 0, then it is Cn. So from here we can write this An, it must be equal to Bn plus Cn. Now this first case, this last digit is 1. If this last digit is 1, then this digit, it can be either 0 or 1. So this entire arrangement is nothing but it is An minus 1. So we can write Bn, it must be equal to An minus 1. Now if we look at this second arrangement, then in this second arrangement we have last digit as 0, and if last digit is 0, then penultimate will be 1. Now this one, it could be either 0 or 1. So it is nothing but it is An minus 2. So this Cn, it is nothing but An minus 2. So from here we can write An equals An minus 1 plus An minus 2, which is the recursive relation for this expression. Now if we look at the second question, then if we put n as 17, we can write A17 will be equal to A16 plus A15. That means this option A, it is correct. Now if we find A1 is this one digit number. This one digit number is simply 1. Now if we look at two digit numbers with 0 and 1 such that two zeros are not possible, it will be 1 0 and 1 1. So A2, it will be 2. So the sequence will be 1 and then 2. 1 plus 2 is 3. 2 plus 3 is 5. 5 plus 3 is 8. 5 plus 8 is 13. Now in this first case, we need to find B6. Now B6 is nothing but it is A5. Now this is A1, A2, A3, A4 and A5. So value of A5 is nothing but 8. So value of B6 is 8, and that's your option B. Now here the question is, if P and Q are randomly chosen from the set 1, 2, 3, 4, 5, 6 with replacement, the number of ways in which this expression, which is x to the power 4 plus px cube plus q plus 1 x square plus px plus q will have positive values for all real x is 2-digit number, then its units place digit is. Now we'll take these two together, and these two together we can write x square, and here will be x square plus px plus q plus x square plus px plus q, which is x square plus 1 into x square plus px plus q, and it should be greater than 0 for all x belongs to R. Now this is always positive, so this quadratic expression, it should be greater than 0, and it will be greater than 0 if d is less than 0. Now d in this case is p square minus 4q, it should be less than 0, or 4q, it must be greater than p square. Now we'll have to look at different combinations of p and q such that this condition is satisfied. Now we look at q, 4q, and the possible values of p. Now value of q can be 1, 2, 3, 4, 5, and 6. Now 4q is 4, 8, 12, 16, 20, and 24. Now corresponding value of p, it can be 1 in this case. Now here it will be 1 and 2, because 1 square and 2 square, it is less than 8. Now here it is 1 square, 2 square, and 3 square. Here also will be 1 square, 2 square, and 3 square. Here will be 1 square, 2 square, 3 square, and 4 square. And here also will be 1 square, 2 square, 3 square, and 4 square. So total number of cases will be 1 plus 2, 3, 3 plus 6, 9, 9 and 8, 17. So there will be 17 such cases, and then its unit place digit is simply 7, and that is the answer to this question. Now the question is, let n1 be less than n2 be less than n3 be less than n4 be less than n5 be positive integers such that n1 plus n2 plus n3 plus n4 plus n5 it is equal to 20. The number of such distinct arrangements is. Now if we take the sum of 1 plus 2 plus 3 plus 4 plus 5, this is n plus 1 by 2, and which is 15. So we are left with 5 such numbers. So here we have 1, it is less than 2, it is less than 3, it is less than 4, and it is less than 5. Now we need to add 5 to these numbers such that n1 plus n2 plus n3 plus n4 it becomes 20. Now one possibility is when this 5 it is added to this 5 itself. So it will be this case when we have added 0, 0, 0, 0, and 5. Now the second case could be when we add 0, 0, 0, and then 1, 4, 0, 0, 0, 2, 3. Now it can also be 0, 0, and then 1, 1, 3, or it could be 0, 0, 1, 2, and 2. Then it could be 0, and this is 1, 1, 1 and 2, and finally it could be this 1, 1, 1, 1 and 1. In each of these cases, n1 will be less than n2, will be less than n3, will be less than n4, and will be less than n5. And there are 7 such cases possible. So number of distinct arrangements is simply 7. And that is the answer to this question. Now here the question is, show that the number of ways in which 3 numbers in AP can be selected from 1, 2, 3 up to n is 1 by 4 n minus 1 square when n is odd, and it is 1 by 4 n n minus 2 if n is even.
Now we'll consider this first case when n is odd. Say n is some 2n plus 1. So we have these numbers from 1, 2, 3 up to 2m plus 1. Now we have to select 3 numbers in AP. Now we can consider 3 numbers with common difference 1. It can be 1, 2, 3, 2, 3, 4 up to 2m minus 1, 2m and 2m plus 1. So there will be 2m minus 1 such numbers with common difference 2. It will be 1, 3, 5, 2, 4, 6, and here it will be 2m minus 3, 2m minus 1 and 2m plus 1. So there will be 2m minus 3 such numbers, and finally numbers whose common difference is m. So it will be 1 and 1 plus m and 2m plus 1 will be simply 1. So number of such APs will be 1 plus 3 plus 5 up to 2m minus 1, which is sum of first m odd natural numbers, and which is nothing but m square, and m in this case is n minus 1 by 2. So total number of such APs will be n minus 1 by 2 whole square. So if n is odd, then it is 1 by 4 into n minus 1 square. Now we'll consider the second case when n is an even number. Now if n is even, say n equals 2m, then we have numbers from 1, 2, 3 up to 2m. Now with common difference 1, we have 1, 2, 3, 2, 3, 4 up to 2m minus 2, 2m minus 1 and 2m, which are 2m minus 2 cases. Now with common difference 2, it will be 1, 3, 5, 2, 4, 6, and here will be 2m minus 4, 2m minus 2 and 2m, and there will be 2m minus 4 cases, and it will continue up to common difference m minus 1. So it will be 1 m, 2m minus 1, and then 2 m plus 1 and 2m. In this case, there will be 2 possibilities. So total number of such APs will be 2 plus 4 plus 6 up to 2m minus 1. So it will be 2, 1 plus 2 plus 3 up to m minus 1. So it will be m plus 1 by 2, which is m into m minus 1. Now m is n by 2, so it will be n by 2 and n by 2 minus 1. So it will be n minus 2 by 4. So if it is even, then it is n minus 2 by 4, and if it is odd, it is 1 by 4 into n minus 1 square.